Subscribe to the channel and like the video. Somewhere, in the vast and unending ocean of the cosmos, exists a star so enormous, so incomprehensibly gigantic, that our mighty sun looks like little more than a glowing grain of sand beside a blazing mountain of fire. Astronomers call it Stephenson 2-18, and this star isn't just large, it's the reigning monarch of stellar giants, stretching the very limits of what we understand about how stars can exist. Imagine something so huge that if placed where our sun currently sits, it would not just swallow Earth, not just engulf Jupiter, but would extend so far out that Saturn itself would be lost within its blazing atmosphere. This is not science fiction, it's science fact. Stephenson 2-18 is, quite literally, the largest star ever discovered, even surpassing the once famous record holder, UY Scuti. When we talk about big things in the universe, black holes and galaxies often steal the spotlight. But stars, those immense nuclear furnaces lighting up the night sky, can grow to mind-bending proportions. And among them, Stephenson 2-18 is the undisputed titan. To put it dramatically, if our sun is a candle, Stephenson 2-18 is a raging bonfire visible from across cosmic continents. Its sheer scale challenges our imagination, forcing us to rethink what it means for something to be big. Now, here's the real hook that should grab your curiosity. Astronomers estimate that if Stephenson 2-18 were hollow inside, it could contain more than 10 billion suns. Think about that for a second. Our sun, the colossal sphere that provides light, warmth, and life to everything on Earth, is utterly dwarfed, almost mocked, by the immensity of Stephenson 2-18. This comparison alone makes you realize just how tiny, how insignificant our corner of the universe really is. So the question naturally arises, what makes this star so fascinating, and why is it so important to study it? It's not just its size, it's the fact that Stephenson 2-18 represents a limit. It shows us how far stars can push physics before collapsing under their own weight. It's like staring at the ultimate boundary line of nature, where gravity, radiation, and cosmic forces are locked in a delicate dance. And we, as observers on a small rocky planet, get the chance to peek at this colossal marvel from nearly 19,000 light-years away. That's the beauty of the universe. It humbles us, excites us, and terrifies us all at once. And Stephenson 2-18 is one of the most extreme examples of that cosmic grandeur. If we really want to understand the staggering immensity of Stephenson 2-18, the best way to do it is to compare it with the one star we all know so well, our sun. After all, the sun is the heart of our solar system, the giver of life. To us, the sun feels impossibly huge already. It's about 1.39 million kilometers across, that's 109 times wider than Earth. In fact, you could line up over 100 Earths side by side just to stretch across the diameter of our sun. And if you think in terms of volume, our sun is vast enough to fit about 1.3 million Earths inside it. That is the scale we use to calling giant. But next to Stephenson 2-18, the sun isn't even worthy of the word. Stephenson 2-18 has an estimated radius around 2,150 times that of the sun. That means its diameter isn't just 1.39 million kilometers, it's over 2.98 billion kilometers across. Let's pause for a second and absorb that number. Nearly 3 billion kilometers. That's so large that if Stephenson 2-18 were placed at the center of our solar system where the sun currently sits, its bloated, fiery surface would stretch out way beyond Jupiter's orbit and nearly touch Saturn's path. Planets we consider distant, like Earth and Mars, wouldn't just be scorched, they would be completely swallowed whole inside the outer atmosphere of this red supergiant. Even Jupiter, the mighty gas giant, would not survive. The sheer physical reach of Stephenson 2-18 is nearly incomprehensible. And it only gets more jaw-dropping when we start talking about volume. The sun, as big as it is, could fit 10 billion times inside Stephenson 2-18. Imagine scooping up 10 billion suns and stuffing them into one single star. That's the kind of cosmic magnitude we're dealing with. And just to really stretch your imagination, if Earth is like a grain of sand, the sun becomes a beach ball, and Stephenson 2-18 becomes a skyscraper taller than Mount Everest stacked hundreds of times. The leap in scale isn't just big, it's insane. Now, when it comes to mass, things get a little counterintuitive. One might think that if Stephenson 2-18 is so much bigger than the sun, it must also weigh billions of times more. But stars don't scale that way. Our Sun contains about 333,000 times the mass of Earth, and Stephenson 2-18, while colossal in size, is only estimated to have between 30 and 40 times the Sun's mass. Think about that contrast: 30 to 40 times the mass, but 10 billion times the volume. What this really tells us is that Stephenson 2-18 is unbelievably diffuse. Its outer layers are so spread out, so expanded, that if you could somehow stand in them, you'd feel like you were floating in an incredibly thin cloud of gas rather than standing on anything solid. The star's density is extraordinarily low, especially compared to compact objects like neutron stars or even our Sun's core. This disparity between size and mass is one of the reasons why Stephenson 2-18 seems to defy common sense. You could almost call it a cosmic balloon, inflated to impossible proportions by the nuclear forces raging at its heart. While our Sun is small, dense, and stable in its middle age, Stephenson 2-18 is a swollen titan nearing the end of its life cycle, puffed up to proportions that challenge our imagination. But to really drive home how shocking this comparison is, let's try to visualize it. Picture the solar system, the Sun sitting at the center, Mercury, Venus, Earth, and Mars orbiting closely around it, then the asteroid belt, then Jupiter, Saturn, Uranus, Neptune, and finally Pluto way out in the icy dark. Now replace the Sun with Stephenson 2-18. Mercury, Venus, Earth, and Mars don't even exist anymore, they're inside the star.
Jupiter, gone. Saturn, engulfed. Uranus,
almost completely consumed as well. Only Neptune and Pluto would be safely outside the star's surface. That's not just larger, that's utterly, devastatingly massive on a scale we almost can't comprehend. And the contrast gets even starker when you think about light travel. Light, which zips around the Earth 7.5 times in a single second, would take over 8 hours just to circle the surface of Stephenson 2-18 once. Meanwhile, it takes just over 8 minutes for sunlight to reach us from our Sun. So, in other words, if you turned on a flashlight at one edge of Stephenson 2-18, someone on the opposite edge wouldn't see it until an entire workday had gone by. That's how unfathomably enormous this star is. So when we compare Stephenson 2-18 to our Sun, it's not just a matter of bigger versus smaller. It's a matter of ordinary versus extraordinary, familiar versus unimaginable. The Sun is enormous to us, but Stephenson 2-18 makes the Sun look like a single glowing speck of dust floating in the middle of an endless night. The difference is so extreme that it bends the limits of human imagination. Now that we've wrapped our heads, at least as much as possible, around the sheer scale of Stephenson 2-18 compared to our Sun, the next natural question is, where exactly is this gargantuan star hiding in the sky? After all, with a size so absurd, you might think it would dominate our night skies like some cosmic beacon. But here's the surprising part: it doesn't. In fact, Stephenson 2-18 sits tucked away in a part of the heavens that isn't particularly well known to casual stargazers. It lies in the constellation Scutum, a faint shield-shaped constellation in the southern celestial hemisphere. Scutum is not one of the famous constellations like Orion or Ursa Major. It's relatively small and dim, and unless you know exactly where to look, you might pass right over it without even realizing. Yet, within this patch of the night sky, about 19,000 light-years away from us, rests the largest star humanity has ever discovered. To put that distance in perspective, light, traveling at 300,000 kilometers per second, takes 8 minutes to reach us from the Sun. But from Stephenson 2-18, it takes like 19,000 years to make the journey. That means the glow we see from this star tonight actually left its surface long before the pyramids of Egypt were built, long before humans discovered agriculture, possibly before humans even existed in their modern form. We're not seeing Stephenson 2-18 as it is now, we're seeing it as it was nearly 20 millennia ago. For all we know, given how unstable and massive it is, the star may have already gone supernova, and we won't witness that cosmic fireworks display until thousands of years from now. Its location within Scutum is not random. Stephenson 2-18 is a member of a star cluster called Stephenson 2, which is packed with red supergiants. This is important because clusters give us a stellar laboratory. They allow astronomers to study groups of stars that were born around the same time, out of the same cloud of gas and dust. By comparing them, scientists can learn about how stars evolve, how they live, and how they die. The cluster itself is hidden behind thick clouds of interstellar dust, which is one of the reasons we can't just look up and see Stephenson 2-18 blazing brightly. That dust dims and reddens the light, making the star look faint from Earth, even though in reality it's shining with a luminosity hundreds of thousands of times greater than our Sun. Scutum itself has an interesting backstory. It was introduced in the late 17th century by the Polish astronomer Johannes Hevelius, who named it Scutum Sobieskianum, Sobieski's shield, after King John III Sobieski of Poland. Today, astronomers simply call it Scutum, the shield. And nestled within this obscure constellation lies one of the greatest treasures of the observable universe, a star so colossal that it stretches the limits of physics. One of the strange and humbling aspects of Stephenson 218's location is that, despite its colossal size, we can't see it with the naked eye. At a distance of 19,000 light-years, its light is simply too diluted by distance and too obscured by dust for our eyes to pick it out. If it were closer, say, as close as Betelgeuse, which is only about 642 light-years away, it would likely dominate our sky, shining as one of the brightest stars visible from Earth. But from its remote vantage point in Scutum, it remains a hidden giant, a titan concealed in the shadows of the galaxy. And here's another fascinating point. Stephenson 2-18 lies in a region of the Milky Way that's rich in stellar activity. This part of the galaxy is teeming with massive clusters, nurseries of stars, and dense molecular clouds. It's as if Stephenson 2-18 was born in the cosmic equivalent of a bustling city, surrounded by other stellar giants, rather than being a lone wanderer like some stars in quieter regions of the galaxy. The fact that it's part of a cluster helps astronomers because its neighbors give them vital reference points for distance, size, and age calculations. So, when you gaze up at the constellation Scutum, though faint and small, you're looking in the direction of one of the most extreme marvels the cosmos has to offer. Imagine pointing your telescope into that unassuming patch of sky and realizing that hidden behind layers of interstellar fog lies the largest star ever found. It's a bit like finding out that in an unremarkable town square there's a skyscraper so tall it could scrape the edges of space. That is the wonder of Stephenson 218's location. Concealed, distant, and yet unbelievably grand. When we think about the discovery of something as immense and extraordinary as Stephenson 2-18, it almost feels strange to imagine that for most of human history, this gigantic star was completely unknown to us. It was sitting there, shining away in the distant reaches of the galaxy, but hidden by distance, dust, and the limitations of our early instruments. Only in the modern era, with advanced telescopes and new ways of peering into the universe, have we been able to uncover its presence. And its discovery isn't the story of one single observation, but rather the gradual unveiling of a whole stellar family, the Stephenson 2 cluster, within which this cosmic titan was hiding. The story begins in the late 20th century with the work of astronomer Charles Bruce Stephenson. In 1990, he published a catalogue of luminous stars that included a group of especially intriguing red supergiants found in the constellation Scutum. These stars seemed to belong to a massive stellar cluster that was previously unrecognized. This cluster came to be known as Stephenson 2, named after him. The cluster itself was important because it contained dozens of red supergiants, more than nearly any other known cluster in the Milky Way. That alone made it a goldmine for astrophysicists who wanted to study the later stages of stellar evolution. It was within this cluster, during more detailed investigations, that Stephenson 2-18 emerged as a standout. Over time, astronomers realized that one of these red supergiants in the cluster wasn't just big, it was absurdly, impossibly big. The initial estimates of its size shocked the astronomical community, and with refined measurements, it eventually took the crown as the largest star ever identified. The -18 in its name designates it as one of the members catalogued within the Stephenson 2 cluster, but it quickly overshadowed its siblings by sheer magnitude. One of the reasons it took so long to identify Stephenson 2-18 properly is because of the cosmic dust between us and the cluster. The Milky Way is full of dark, dusty clouds that block and scatter visible light, making it difficult to see distant objects clearly. If astronomers had relied only on traditional optical telescopes, Stephenson 2-18 might have remained hidden indefinitely. But advances in infrared astronomy allowed scientists to cut through that obscuring dust and reveal the true nature of the stars inside Stephenson 2. Infrared light travels more easily through interstellar dust than visible light, so by shifting our eyes to this part of the spectrum, astronomers could suddenly uncover stars that had been cloaked for centuries. When Stephenson 2-18 was carefully analyzed, astronomers realized they were looking at something exceptional. Its apparent brightness, even after being dimmed by dust, suggested extreme luminosity. And when they calculated its radius, the numbers seemed almost unbelievable, more than 2,000 times the radius of our Sun. At first, there was some hesitation. After all, measuring the size of stars at such distances is notoriously difficult. But as more observations were made, the evidence solidified. Stephenson 2-18 wasn't just a red supergiant. It was the red supergiant, the largest one we had ever found. The discovery of Stephenson 2-18 within its cluster also added to the importance of Stephenson 2 as a whole. Here was a stellar nursery that had produced an entire family of massive stars, many of them already bloated into red supergiants. And among them, one stood head and shoulders above the rest. This cluster, located around 19,000 light-years from Earth, suddenly became one of the most fascinating stellar laboratories in the galaxy. By studying the stars within it, especially the colossal Stephenson 2-18, astronomers could gain insights into the lives and deaths of the most massive stars the universe has to offer. It's worth noting that discoveries like this are rarely the work of a single individual. While Stephenson first brought attention to the cluster, the detailed study of Stephenson 2-18 came through decades of work by multiple teams of astronomers using a range of instruments. Observations from infrared surveys, follow-up studies with large ground-based telescopes, and refinements in stellar modeling all contributed to piecing together the puzzle. Each step peeled away a layer of mystery until the true size and nature of the star were revealed. And just as remarkable as the discovery itself is the thought of how many more giants might still be lurking out there, hidden by dust or distance, waiting to be uncovered with the next generation of telescopes. Stephenson 2-18 may be the biggest star we know about now, but the universe is vast and full of secrets. Its discovery reminds us that even in the age of modern astronomy, there are still record-shattering marvels to be found. When we talk about Stephenson 2-18's size, we're not just tossing around impressive numbers for the sake of drama. The scale of this star is genuinely mind-bending, pushing the limits of what a human brain can reasonably imagine. Astronomers estimate that Stephenson 2-18 has a radius roughly 2,150 times that of our Sun. That single number alone is almost too large to wrap our heads around, so let's break it down in ways that make sense. Our Sun, as enormous as it already is, has a radius of about 696,000 kilometers. That means if you were to take a spacecraft traveling at the speed of a modern jet airliner, say 900 kilometers per hour, it would take you around 52 days of continuous flying just to circle around the Sun one time. Now multiply that radius by 2,150. Suddenly, Stephenson 2-18 stretches out to a radius of nearly 1.5 billion kilometers. That's not diameter, that's just the radius. If you wanted to travel around the entire circumference of Stephenson 2-18 at that same airplane speed, you'd be flying non-stop for over 900 years before you made it back to where you started. That's the kind of scale we're dealing with. To visualize it in another way, imagine placing Stephenson 2-18 where our Sun currently sits in the middle of the solar system. Its surface would not stop near Earth, or Mars, or even Jupiter. Instead, its bloated atmosphere would extend so far outward that Saturn, our magnificent ringed planet, orbiting at nearly 1.5 billion kilometers from the Sun, would be deep inside the star itself. This means that the entire inner solar system, plus the gas giants Jupiter and Saturn, would be swallowed whole within the body of this single star. Only Uranus and Neptune, way out at the icy edges of our solar system, would remain outside the star's fiery surface. It's like imagining a single campfire that suddenly grows so large it engulfs an entire city, then an entire country, and then half the world. The scale is outrageous. But let's not forget volume. When astronomers say Stephenson 2-18 is 2,150 times the radius of the Sun, that doesn't just mean it's 2,150 times bigger. Size scales differently with radius. The volume of a sphere increases with the cube of the radius, so a star that's over 2,000 times the radius of the Sun ends up with a volume over 10 billion times greater than the Sun's. That's why astronomers say you could fit more than 10 billion suns inside Stephenson 2-18. Think of our Sun as a single grain of rice. Now picture an entire mountain range made entirely of rice grains. Stephenson 2-18 is the mountain range, and the Sun is the lone grain. That's the level of disproportion we're looking at. And yet, despite all this size, Stephenson 2-18 is not the most massive star. That's the kicker. You might expect something so large to weigh 1,000 times more than the Sun, but in reality, its mass is only estimated at 30 to 40 solar masses. That means it's only 30 to 40 times heavier than the Sun, despite being 10 billion times bigger in volume. The reason is that stars like Stephenson 2-18 are incredibly diffuse. Their outer layers are spread so thin that they're more like vast cosmic clouds than dense, compact objects. If you could somehow scoop up a cubic kilometer of its outer atmosphere, it would weigh far less than the same volume of Earth's air. That's why astronomers sometimes describe red supergiants like Stephenson 2-18 as puffed-up balloons of gas rather than solid bodies. Another fascinating aspect of its size is how it interacts with physics itself. Stars can only expand so far before the balance between gravity pulling inward and radiation pressure pushing outward starts to falter. Stephenson 2-18 is hovering right at the edge of that balance. Its enormous radius is a sign that it's in the late stages of its life, burning through its fuel in a desperate struggle to maintain equilibrium. Stars don't get much larger than this, because beyond a certain point, the outer layers can't be held in place anymore. They blow off into space, or the star collapses in a catastrophic supernova. So Stephenson 2-18 is not just big, it's nearly as big as the laws of physics will allow a star to be. What's really remarkable is how astronomers can even measure something so far away and so large. They do it by combining measurements of brightness, distance, and spectrum. By studying the light that reaches us and comparing it to models of stellar atmospheres, they can estimate the star's luminosity and temperature. From there, they calculate its radius. And every time they've done this for Stephenson 2-18, the results have consistently confirmed its staggering size. So when we say Stephenson 2-18 has a radius of 2,150 times the Sun's, we're not just stating a fact. We're describing an object so immense that it rewrites the meaning of big in our universe. It's a cosmic giant sitting at the outer limits of stellar physics, a bloated, fiery balloon so huge it could swallow half our solar system without effort. And yet, fragile too, because a star that large can't live for long. For a long time, the name UY Scuti reigned supreme whenever astronomers or science enthusiasts talked about the biggest star in the universe. This red supergiant, located in the constellation Scutum as well, was widely recognized as the largest star humanity had discovered. It was almost a household name among astronomy fans, an icon of cosmic enormity, used in documentaries, classroom lectures, and countless YouTube videos to demonstrate the staggering scale of the universe. For years, UY Scuti held the crown with an estimated radius of around 1,700 times that of the Sun, making it so vast that it would stretch beyond the orbit of Jupiter if placed at the center of our solar system. But in the grand theater of science, records are always waiting to be broken. Enter Stephenson 2-18, a star that didn't just nudge UY Scuti out of the top spot, it obliterated its lead with a size that's on another level entirely. At a radius of around 2,150 times that of the Sun, Stephenson 2-18 is not just larger than UY Scuti, it's significantly larger, by hundreds of solar radii. That difference might sound small in everyday terms, but in the cosmic arena, it's like comparing a mountain to a continent. If UY Scuti could engulf Jupiter, Stephenson 2-18 swallows Saturn and pushes dangerously close to Uranus. The leap in size is breathtaking. The dethroning happened because of more refined observations and better data analysis. For many years, the title of largest star was somewhat debated, because measuring the size of these colossal red supergiants is incredibly difficult. They don't have sharp edges the way a planet does. Instead, their atmospheres are extended, fuzzy, and constantly shifting. Their outer layers are made of turbulent, convective gases, and their brightness fluctuates over time. Imagine trying to measure the size of a campfire from 20 miles away. You can see the glow, but where exactly does the fire end? That's the challenge astronomers face when dealing with these stars. For UY Scuti, early estimates placed its radius at about 1,700 times the Sun's, but those calculations came with large uncertainties. As instruments improved, and as scientists began using more advanced infrared surveys to cut through the dust obscuring distant stars, a new giant revealed itself in the same constellation, Stephenson 2-18. When its light was analyzed and compared against stellar models, the numbers were shocking. At first, some astronomers thought the data might be overestimated. Surely no star could be that big. But further confirmation came, and slowly the consensus formed. Stephenson 2-18 was indeed larger than UY Scuti, and not just by a small margin. One of the key reasons Stephenson 2-18 outshined UY Scuti is its placement in the Stephenson 2 cluster, which gave astronomers a more reliable frame of reference. Clusters are immensely helpful because all the stars within them are roughly the same age and distance from Earth. This means scientists can compare them against each other and reduce the margin of error when calculating size. UY Scuti, by contrast, is somewhat more isolated, making its exact dimensions harder to pin down with absolute certainty. Now, let's make this more tangible with a solar system comparison. Place UY Scuti at the center of our solar system. Earth, Mars, Jupiter, they're all gone inside the star's enormous radius. Saturn, however, would just barely escape, orbiting near the outer atmosphere. But with Stephenson 2-18 in the Sun's place, Saturn is gone too. Its rings, its moons, its beautiful banded clouds, everything would be consumed. Uranus would orbit dangerously close to the stellar surface, and Neptune would finally be the only planet safe from total engulfment. That extra reach between UY Scuti and Stephenson 2-18 may not sound massive when you're just hearing numbers, but in terms of planetary real estate, it makes the difference between losing Saturn or keeping it. This dethroning also reshaped the way astronomers talk about the biggest star. For years, UY Scuti was the go-to example, but as Stephenson 2-18 took its crown, science communicators had to update diagrams, lectures, and videos. It became a humbling reminder that astronomy is not static, it evolves. Our understanding of the universe shifts with every new piece of data, and what we consider the largest star today may not hold the title tomorrow. In essence, Stephenson 2-18 dethroned UY Scuti because of better measurement, improved observation techniques, and the advantage of being in a cluster where its size could be checked against its peers. It wasn't just an accidental discovery, it was a revolution in how we look at stellar giants. And it set a new benchmark for the scale of stars, forcing us to stretch our imaginations even further. Trying to truly picture the size of Stephenson 2-18 is like trying to imagine infinity. It slips through the cracks of our normal sense of scale. Numbers like 2,150 times the radius of the Sun, or 10 billion times the Sun's volume are impressive on paper, but they don't land with the gut punch of reality until we bring them into the context of our own solar system. So, let's play with some analogies and visualizations to make this star's sheer enormity more relatable, even if only in glimpses. Start by placing Stephenson 2-18 where our Sun currently sits. Immediately, Mercury, Venus, Earth, and Mars vanish without a trace. They don't just burn up, they're swallowed whole, their orbits erased as they sink into the star's seething layers of gas. Jupiter, the king of planets, with its stormy stripes and its swirling great red spot, doesn't last either. It, too, falls victim to the star's sheer immensity. But unlike UY Scuti, which just barely leaves Saturn safe, Stephenson 2-18 stretches even further, extending so far outward that Saturn itself, with its gorgeous, iconic rings, finds itself deep inside the star's fiery outer atmosphere. Imagine those rings, which today gleam like a cosmic crown, completely dissolving in a sea of superheated plasma. Now picture Uranus, that icy blue-green world tipped on its side, orbiting only a hair's breadth beyond the bloated stellar surface. If Stephenson 2-18 were just slightly larger, even Uranus would be inside its envelope. Only Neptune, the outermost of the main planets, would circle just outside the star's swollen edges, orbiting precariously close to a cosmic furnace so large it would dominate every inch of our sky. For comparison, the Sun in our sky takes up about half a degree of arc. It looks roughly the size of a coin held at arm's length. But if Stephenson 2-18 replaced our Sun, the star would cover nearly the entire sky. Day and night as we know them would be obliterated, because the star's glowing expanse would stretch horizon to horizon. And here's another way to think about its volume. If Stephenson 2-18 were hollow, you could pour over 10 billion suns inside it. 10 billion. Think of how absurdly huge our Sun feels to us. It's so massive it holds 99.8% of all the mass in the solar system. Now imagine stuffing 10 billion of them inside one star. It's such an extreme comparison that it almost stops feeling real. To make it even more dramatic, if Earth were a tiny marble, the Sun would be about the size of a large yoga ball next to it. But Stephenson 2-18 would be like a massive hot air balloon so large it could engulf an entire city skyline along with that yoga ball, and then still have room to spare. Let's stretch the analogy even further. Suppose you're sitting in a car, and you drive around the Sun's circumference at a highway speed of 100 kilometers per hour. You'd be driving for about 160 years non-stop to complete a single lap. Now, try the same road trip around Stephenson 2-18. Buckle in for the longest ride of your life, because you'd be at the wheel for more than 300,000 years before you finally made it back to where you started. 100 generations of humanity would live and die before your journey ended. That's the level of incomprehensible size we're dealing with. And then there's light itself, the fastest thing in the universe. Light can circle our Sun in just over 14 seconds. But when it comes to Stephenson 2-18, light would need over 8 hours to complete one lap around its equator. Imagine sending a message around the star at the speed of light. It wouldn't return until you'd had breakfast, lunch, and dinner. In the timescale of light, the ultimate speed demon, that's an eternity. Here's another fun way to think of it. If you were to replace the Sun with Stephenson 2-18 and somehow survive the blazing inferno, the star would appear so large in the sky that its surface would look like it was sitting right above your head, almost close enough to touch. Our entire sky would be one constant ocean of fire and glowing clouds of gas. Constellations? Gone. Nighttime? Gone. The stars we use to navigate, the galaxies we admire, the Milky Way stretching across the heavens, all of it would be erased by the overwhelming presence of one single star. So when astronomers say Stephenson 2-18 would engulf Saturn or extend beyond, they aren't being poetic, they're being literal. If this monster of a star were dropped into our solar system, everything, from Mercury all the way out to Saturn, would cease to exist as separate bodies. They'd simply become part of the star. And for us, standing on what used to be Earth, the universe as we know it would disappear behind a wall of stellar fire so vast it defies comprehension. When we talk about stars, size is one thing, but brightness, luminosity, is another level of or altogether. Because Stephenson 2-18 isn't just the biggest star we've ever found, it's also one of the most luminous stars in the Milky Way galaxy. Its light output is staggering, so overwhelming that even though it sits buried 19,000 light-years away and hidden behind thick clouds of interstellar dust, it still manages to shine through to our telescopes with undeniable force. Let's start with some numbers. Our Sun, the star that sustains all life on Earth, gives off about 3.8x10 squared watts of energy. That's 380 sextillion watts, so much power that every single second, it produces more energy than humanity has consumed in our entire existence. It's dazzling, almost incomprehensible. And yet, Stephenson 2-18 puts our Sun completely to shame. Astronomers estimate that it radiates nearly 440,000 times more light than the Sun. Yes, nearly 500,000 suns worth of brilliance, streaming into the galaxy from a single star. Think about that. If our Sun were replaced with Stephenson 2-18, the Earth would not just be scorched, it would be annihilated almost instantly. Its luminosity is so great that the delicate balance sustaining planets in the habitable zone would be obliterated. Even Pluto, way out at the frozen edge of the solar system, would be blasted with more energy than Earth receives from the Sun today. Every corner of our solar system would glow under the relentless intensity of its radiation. But here's where things get even more intriguing. Despite being so luminous, Stephenson 2-18 isn't actually that hot on its surface compared to smaller stars. Its surface temperature is only about 3,200 Kelvin, which is cooler than the Sun's surface temperature of 5,778 Kelvin. That's why Stephenson 2-18 glows a deep red, while the Sun shines a bright yellow-white. Yet, because Stephenson 2-18 is so unbelievably enormous, the total amount of energy it emits is magnified to a degree that utterly dwarfs the Sun's size beats temperature here. The bigger the surface area, the more light escapes into space, even if each square meter of its surface isn't as intense as the Sun's. To picture its luminosity, let's try a little thought experiment. Imagine a dark night on Earth with the moon in the sky. The full moon reflects sunlight toward us, shining with a brightness we can easily see, even strong enough to cast shadows. But the full moon is about 400,000 times dimmer than the sun. Now picture a star that is 440,000 times brighter than the sun itself. That's Stephenson 2-18. If it were close enough, it would dominate our sky in a way no human has ever witnessed before. It would turn night into a permanent day, brighter than anything we could ever imagine. And yet, for all that brilliance, we don't see it in our night sky. Why? Because distance is a cruel filter. Sitting nearly 19,000 light-years away, and heavily obscured by the Milky Way's interstellar dust, much of its light is absorbed or scattered before it ever reaches us. If we could strip away the dust and bring the star even a little closer, it would shine as one of the most dazzling objects in the heavens, outshining Betelgeuse, Rigel, or even Sirius, the brightest star we see today. In fact, if Stephenson 2-18 were placed just 1,000 light-years from Earth, it would likely appear as bright as a crescent moon in the night sky. Imagine looking up and seeing a red, glowing beacon so vivid that it outshines every other star by orders of magnitude. That's the raw power of its luminosity. There's also an eerie thought hidden in its brightness. The light we see now left Stephenson 2-18 nearly 19,000 years ago. In human terms, that's before the rise of written history. What we're observing is ancient light from a star that may already have changed dramatically. It could be dimmer now, swollen larger, or it may even have already exploded in a titanic supernova, its brilliance scattered across the cosmos. But for us, locked into the flow of light and time, it remains a blazing beacon of the ancient universe. Brightness also tells us something about the internal mechanics of the star. A luminosity of this scale is a warning sign. Stars that bright burn through their nuclear fuel at an insane rate. Where our sun has a stable lifespan of about 10 billion years, Stephenson 2-18 will only live for a few million. It's shining so fiercely because it's burning itself out, like a candle flame roaring bright just before it gutters out. Its luminosity is both its crown and its curse. It is the very reason it cannot last long. So, when you hear that Stephenson 2-18 is 440,000 times more luminous than our sun, don't just file it away as another statistic. Think of a sun so powerful that it could turn Pluto into a warm, balmy world. Think of a star so radiant that it could erase the concept of night sky altogether if it were just a little closer. And most of all, think of the incredible paradox of something so massive, so bright, and so ancient sitting invisibly in our galaxy, unnoticed to the naked eye, but blazing away with a fury that dwarfs our entire solar system. When we call Stephenson 2-18 a red supergiant, we're not just throwing in an impressive-sounding label. That phrase carries with it a very specific meaning in the world of astronomy, one that explains exactly why this star has swollen to such monstrous proportions and why its very existence is a clue about where it is in its life cycle. To understand Stephenson 2-18, you first have to understand what it means for a star to wear the title of red supergiant. A star's life is dictated almost entirely by its mass. Small stars, like red dwarfs, burn their fuel slowly and can live for trillions of years, barely changing their appearance. Medium-sized stars, like our sun, burn steadily for billions of years before expanding into red giants and eventually collapsing into white dwarfs. But the most massive stars, the true heavyweights of the universe, live fast and die young. They blaze through their fuel at breakneck speed, and when they near the end of their short lifespans, they expand into the enormous, bloated objects we call red supergiants. So what is a red supergiant, exactly? It's the final, swollen phase in the life of a massive star. After spending millions of years fusing hydrogen into helium in its core, a star like Stephenson 2-18 eventually exhausts that hydrogen fuel. The core begins to contract under gravity, heating up enough to start fusing heavier elements like helium into carbon and oxygen. As the core changes, the outer layers respond dramatically. They balloon outward, expanding to hundreds or even thousands of times the star's original size. The outer layers cool as they spread, giving the star its characteristic reddish glow. That's why we call them red supergiants. They are massive stars, swollen to impossible sizes, with cooler outer atmospheres that shine in shades of orange and red. Stephenson 2-18 belongs firmly in this category. Its surface temperature of about 3,200 Kelvin is much cooler than the Sun's, which is why it shines with a reddish hue. Its bloated radius, more than 2,000 times that of the Sun, fits the red supergiant profile perfectly. And its luminosity, hundreds of thousands of times greater than our Sun, is exactly what you'd expect from a star at this stage of evolution. Everything about Stephenson 2-18 screams red supergiant. But there's another nuance. Supergiants are not just big, they're unstable. Unlike our Sun, which has a calm, steady balance of gravity and nuclear pressure, red supergiants are in turmoil. Their outer layers are tenuously bound, almost drifting into space, and often shed material in powerful stellar winds. In fact, Stephenson 2-18 is likely losing mass at a staggering rate right now, ejecting huge amounts of gas and dust into the surrounding space. This is part of the reason why the cluster it resides in is shrouded with interstellar material. You could say Stephenson 2-18 is bleeding out as it nears the end of its cosmic life, painting its neighborhood with the raw materials for future stars. One of the most famous red supergiants visible to us is Betelgeuse, the bright red star marking Orion's shoulder. Betelgeuse is massive, bloated, and unstable, an icon of the red supergiant stage. Yet, when compared to Stephenson 2-18, Betelgeuse looks small. Where Betelgeuse might engulf the orbit of Jupiter if placed in our solar system, Stephenson 2-18 swallows Saturn and nearly Uranus. They both share the same category, but Stephenson 2-18 represents the extreme limit of what a red supergiant can become. It's like comparing a tall basketball player to a skyscraper. Both are tall, but one redefines the word entirely. The super in supergiant isn't an exaggeration either. Red supergiants are the largest stars in terms of physical size, even though they're not always the most massive. Their sheer volume makes them unmatched in scale. But their low surface temperature, compared to blue giants or main sequence stars, gives them that distinctive reddish tint. They are, quite literally, gigantic, cool, and luminous stars on the edge of stellar death. Stephenson 2-18 also highlights something fascinating about stellar physics, the delicate balance between gravity and radiation. A star only maintains its shape because its core is pushing outward with the pressure of nuclear fusion, while gravity tries to pull everything inward. In a red supergiant, the balance is tipped toward instability. The outer layers are barely held in place, stretched out across billions of kilometers, constantly trembling and convecting like a boiling pot of water. That's why their atmospheres are so hard to define. The surface isn't a sharp boundary, but more of a diffuse, turbulent fog of glowing gases. So, when astronomers say Stephenson 2-18 is a red supergiant, they're telling us this. Here is a star in its final act, a bloated colossus burning through the last stages of its fuel, swelling to cosmic dimensions as it prepares for its spectacular and inevitable death. Its redness marks its cooling surface, its enormous size marks its unstable expansion, and its supergiant classification tells us it's one of the largest stars that physics will allow. Stephenson 2-18 is not unique in being a red supergiant, but it is unique in being the largest one we've ever measured. It is the king among kings in this category, standing at the very edge of possibility. And that alone makes its existence both awe-inspiring and sobering, because stars in this phase are fleeting. It is a reminder that even the mightiest of cosmic giants are temporary. One of the strangest and most counterintuitive facts about Stephenson 2-18 is that, despite being the largest star ever discovered, its surface is actually cooler than our Sun's. At first, that sounds impossible. Shouldn't something so gigantic burn hotter, brighter, and more intensely? But in truth, this is one of those cosmic paradoxes that makes astronomy so endlessly fascinating. Let's put the numbers on the table. The surface of our Sun sits at about 5,778 Kelvin. That's nearly 10,000 degrees Fahrenheit. It's hot enough to make hydrogen atoms smash together into helium, releasing immense amounts of energy in the process. This temperature gives the Sun its yellow-white glow. Now, Stephenson 2-18, despite being thousands of times larger, has a surface temperature of only around 3,200 Kelvin. That's just a little over 5,000 degrees Fahrenheit, cooler even than some types of welding flames. On the cosmic temperature scale, it's downright chilly for a star. And this is exactly why it looks red. Stars shine different colors based on their surface temperature. The hottest stars burn with a bluish hue, like Rigel in Orion, with temperatures soaring above 20,000 Kelvin. Slightly cooler stars, like our Sun, glow white or yellow. Cooler still, stars around 3,000 to 3,500 Kelvin glow in shades of orange or deep red. That's where Stephenson 2 to 18 lands. Its outer layers are so distended and spread out that their energy output per square meter is much weaker, and so its glow appears red. The real reason for this cooler surface lies in the sheer scale of the star. When Stephenson 2 to 18 expanded into its red supergiant phase, its outer atmosphere ballooned outward billions of kilometers. The farther that atmosphere spreads, the more diffuse and thin it becomes. Imagine blowing up a balloon. The more you inflate it, the thinner and weaker its skin gets. The same is true for the surface layers of a star. As the outer layers stretch outward, they cool, creating that distinct red glow. So here's the paradox. Although Stephenson 2 to 18 is cooler at the surface than our Sun, its total energy output is far greater. That's because while each square meter of its surface is less intense, it has so many more square meters of surface area that the total luminosity skyrockets. To put it another way, our Sun is like a small but incredibly hot stove burner, while Stephenson 2 to 18 is like a massive campfire. It's cooler when you touch the flames, but it covers such a vast area that the total heat radiated is incomparably greater. Another fascinating thing about the low surface temperature is what it tells us about the star's internal structure. Deep inside, Stephenson 218's core is unimaginably hot, likely tens of millions of degrees Kelvin, hot enough to fuse heavier and heavier elements. But the outer layers are so bloated and extended that the energy has to travel an enormous distance to escape. By the time it reaches the star's visible surface, that energy has dissipated, and the temperature has dropped significantly. It's a bit like heating water at the bottom of a giant pot. The bottom boils furiously, but by the time the heat reaches the very top, the water there is cooler and calmer. There's also the fact that the star's surface isn't really solid or even well-defined. When astronomers measure the temperature of a red supergiant like Stephenson 2 to 18, what they're really talking about is the temperature of its photosphere, the thin layer from which most of the visible light escapes. But this layer is not a sharp boundary like a planet's crust. Instead, it's a fuzzy, turbulent ocean of plasma, constantly boiling and convecting. Giant cells of gas the size of entire planets churn and bubble across its surface, rising and falling in slow motion. This makes the actual surface appearance variable, uneven, and almost storm-like. So when we say 3200 Kelvin, it's an average, a simplification of a surface that is far from simple. The cooler surface temperature also hints at instability. Red supergiants like Stephenson 2 to 18 often fluctuate in brightness because their outer layers are so thinly spread that they pulse in and out. They literally breathe, expanding and contracting as pressure waves ripple through their atmospheres. These variations can change their surface temperature slightly over time, which in turn alters their color and brightness. So, Stephenson 218's reddish glow may not always be the same. It's a living, changing thing, shifting as the star nears its end. If Stephenson 2 to 18 were close enough to see with the naked eye, its color would be stunning. Instead of the bright white sparkle we associate with many stars, it would appear as a giant ruby hanging in the sky. You'd see a deep, fiery red, glowing faintly but steadily, dwarfing every other star around it. Betelgeuse, one of the most famous red stars in the night sky, would pale in comparison to this crimson titan. And here's a fun thought experiment. If you could somehow stand just outside the bloated surface of Stephenson 2 to 18, you'd be looking at plasma so cool, by stellar standards, that it wouldn't instantly vaporize you in the same way our Sun's photosphere would. Of course, the radiation pressure and sheer energy output would still obliterate you instantly. But compared to the Sun, the light would feel less searing, even though it's vastly more abundant. Again, that strange paradox of coolness masking unimaginable power. So, the fact that Stephenson 2 to 18 glows at only 3200 Kelvin doesn't make it less impressive, it makes it more mysterious. It shows us that size and heat don't always go hand in hand. You can have the largest star in the known universe, and yet it shines with the same hue as a dying ember in a campfire. That ember, however, is so large it could swallow entire solar systems. Stephenson 2 to 18 is not a lonely wanderer in the cosmos. It belongs to a vast community of stars bound together by gravity, known as the Stephenson 2 cluster. And this detail is far more important than it might sound at first, because clusters like this one act as natural laboratories for astronomers. They allow us to study how stars form, evolve, and die, not in isolation, but in groups that were born together from the same gigantic cloud of gas and dust. The Stephenson 2 cluster is also called RSGC2, which stands for Red Supergiant Cluster 2. That name already gives away something special. It contains a remarkably large number of red supergiants. Most star clusters don't have many of these colossal stars because they're so rare. Massive stars burn through their lives quickly, and the red supergiant phase lasts only a blink of an eye in cosmic terms, maybe 1,000,000 years or less. For us to catch a cluster filled with so many of them at once is like stumbling upon a fireworks show at the exact moment every firework is exploding in the sky. It's fleeting, spectacular, and scientifically priceless. This cluster lies in the constellation Scutum, about 19,000 light-years away from Earth, tucked within the disk of the Milky Way. The galaxy's disk is crowded, dusty, and messy, which makes spotting clusters like this a challenge. Much of the light from Stephenson 2 and its sibling stars is obscured by interstellar dust, so they don't shine brightly in visible wavelengths. That's why astronomers often turn to infrared observations. Infrared light can cut through the dust and reveal these hidden giants. Without infrared astronomy, we might not even know the Stephenson 2 cluster exists, let alone that it contains the largest known star in the universe. Now, why is this cluster so special? For one, it's massive. Astronomers estimate that Stephenson 2 contains tens of thousands of stars, possibly more, with a total mass many times greater than that of typical open clusters. But more importantly, it contains over 24 known red supergiants, the largest single collection of them found in the Milky Way. To put that into perspective, our galaxy has roughly 200 billion stars, yet red supergiants are so rare that you could search vast stretches of space and find only one or two at a time. For Stephenson 2 to have so many gathered in one place is extraordinary. The presence of so many red supergiants also tells astronomers something crucial about the cluster's age. Stars in a cluster all form around the same time, from the same giant molecular cloud. By studying which types of stars are present, scientists can estimate the cluster's age. In the case of Stephenson 2, the fact that so many massive stars have already evolved into red supergiants suggests the cluster is somewhere between 10 to 20 million years old. That's incredibly young by cosmic standards. Our own Sun, for comparison, is about 4.6 billion years old. In other words, Stephenson 2 is like a stellar kindergarten class, full of young but oversized kids that grew up too fast. Clusters like Stephenson 2 are also valuable because they give us a kind of controlled experiment. Since all the stars formed at roughly the same time and from the same material, any differences we see among them can be attributed mostly to their masses. That means astronomers can compare a lower mass star in the cluster to a higher mass star, like Stephenson 2 to 18, and directly observe how mass affects a star's evolution. It's rare in astronomy to have such a neat setup, since most stars we study are scattered across space, born at different times, from different nebulae, under different conditions. Stephenson 2 simplifies the variables. And then there's the dramatic future awaiting this cluster. Every red supergiant in Stephenson 2, including Stephenson 2 to 18, is a ticking time bomb. Within the next few million years, a blink in galactic terms, many of these giants will explode as supernovae. That means Stephenson 2 is destined to become one of the most violent regions of the galaxy, filling its corner of Scutum with shockwaves, radiation, and clouds of heavy elements. Those elements, carbon, oxygen, silicon, iron, will enrich the surrounding interstellar medium, seeding the material for new generations of stars and planets. Some of the atoms in our own bodies, like the iron in our blood, were forged in such explosions billions of years ago. Watching Stephenson 2 is like watching the very cycle of cosmic recycling in action. What's also fascinating is that this cluster helps us test the upper limits of stellar size. Because it contains not just Stephenson 2 to 18 but many other large red supergiants, astronomers can compare them and refine their models of how stars expand in this late phase of life. How big can a star realistically get before it collapses under its own gravity? Why do some red supergiants stop at the size of Betelgeuse, while others balloon out to swallow the orbit of Saturn? The answers may lie in clusters like this, where dozens of giant stars evolve in parallel. The Stephenson 2 cluster is hidden, shrouded in cosmic dust, and yet it may be one of the most important stellar nurseries we've ever identified. It's like stumbling upon a hidden vault of treasures buried in the galaxy, a vault filled not with gold, but with colossal stars on the verge of their grand finale. And at the heart of this vault sits Stephenson 2 to 18, the undisputed ruler of them all, towering above its siblings in sheer size. So, when we talk about Stephenson 2-18, we're not just talking about a star, we're talking about the family it belongs to, a family that has given astronomers a rare and extraordinary glimpse into how the most massive stars live and die. Without its cluster, Stephenson 2-18 might have been nearly impossible to discover. With its cluster, it becomes part of a bigger story, one of cosmic creation, destruction, and renewal. Measuring the size of a star like Stephenson 2-18 sounds simple in theory. Point a telescope at it, figure out how big it looks, and calculate its size. But the reality is far trickier. Unlike planets, which have solid surfaces and sharp edges, stars are giant glowing balls of plasma with no hard boundary. Their surface is really just the outermost layer where the gas becomes transparent enough for light to escape, called the photosphere. That means astronomers are essentially trying to measure a fuzzy ball of gas from tens of thousands of trillions of kilometers away. And when that star happens to be 19,000 light-years away and buried behind clouds of interstellar dust, the challenge becomes monumental. So how do astronomers do it? The process relies on a combination of light, distance, and models. First, they measure the star's apparent brightness, how much light reaches Earth. But brightness alone doesn't tell us the whole story. A small but close star can look as bright as a massive but distant one. To separate those two effects, astronomers need to know the star's distance. Once they have both the brightness and the distance, they can calculate the star's luminosity, the true power it emits in all directions. Next comes the color of the star's light. By analyzing the spectrum, astronomers can determine its temperature. The star's light contains fingerprints of the elements in its atmosphere, and the shape of the spectrum reveals how hot the surface is. This is where Stephenson 2-18's relatively cool 3200 Kelvin comes into play. Now, with luminosity and temperature in hand, scientists can apply a physical relationship known as the Stefan-Boltzmann law. This law links a star's luminosity, radius, and surface temperature. In simplified terms, it says that a star's luminosity equals the surface area of the star multiplied by the energy emitted per unit area. Since the energy per unit area depends on the temperature, astronomers can rearrange the equation to solve for the radius. The result is a staggering number. Stephenson 2-18 has a radius over 2,150 times larger than the Sun. But here's the catch: the farther away a star is, and the more dust between us and it, the more uncertain these measurements become. Interstellar dust dims and reddens starlight, making the star look cooler and fainter than it really is. To correct for that, astronomers use infrared observations, which can pass through dust more effectively. Instruments like those on the Very Large Telescope, VLT, in Chile and the Spitzer Space Telescope in orbit have been key to peering through the haze and refining measurements of stars like Stephenson 2-18. Another approach astronomers sometimes use for closer giants is interferometry. This technique combines the light from multiple telescopes spread out over large distances to create a kind of super telescope with far higher resolution than a single one could achieve. With interferometry, scientists have been able to directly resolve the disks of some nearby supergiants like Betelgeuse, actually measuring their angular size in the sky. Unfortunately, Stephenson 2-18 is too far and too obscured to resolve directly with current instruments, but similar techniques on future telescopes might make it possible. There's also the problem of variability. Red supergiants like Stephenson 2-18 don't have perfectly stable surfaces. They pulsate, expand, and contract over time. Huge convection cells churn across their photospheres, sometimes changing the measured brightness and temperature. That means the size we assign to Stephenson 2-18 is an estimate, not a perfectly fixed number. Depending on when you measure it, the calculated radius might shift by hundreds of solar radii. It's a bit like trying to measure the width of an ocean wave. You can get a good average, but the surface is always moving. And then, astronomers must also decide what counts as the edge of the star. Because its outer layers are so thin and diffuse, Stephenson 2-18 doesn't stop abruptly like a planet does. Its atmosphere trails off gradually into space, merging with the vacuum. Different techniques might define the radius at different depths, where the light escapes, where the density drops off, or where infrared observations become transparent. Each choice gives slightly different answers, which is why you'll sometimes see varying numbers in scientific papers about the star's size. In short, measuring the size of a star like Stephenson 2 to 18 is a delicate balance of careful observation, physics equations, and a lot of error correction. It's not like holding up a ruler. It's more like piecing together a puzzle from dim and distorted clues scattered across the electromagnetic spectrum. Yet, despite all those hurdles, astronomers are confident enough in their methods to say that Stephenson 2 to 18 is currently the largest star ever identified, dethroning UY Scuti and other contenders. It's humbling to realize that, from nearly 20,000 light-years away, humans have been able to deduce the size of something so gigantic that it defies ordinary comprehension. It shows the power of science, not to physically touch the stars, but to use light itself as the measuring tape of the cosmos. When we talk about Stephenson 2 to 18, we're looking at a star in the twilight of its life. To truly appreciate just how dramatic its current stage is, we need to zoom out and look at the life cycle of massive stars, because unlike our Sun, which will live for billions of years in relative stability, a star like Stephenson 2 to 18 burns fast and dies young. Every star begins the same way, as a clump of gas and dust collapsing under its own gravity inside a molecular cloud. As the cloud contracts, it heats up until nuclear fusion ignites in the core, converting hydrogen into helium. That's the moment a star is born, entering what astronomers call the main sequence, a long, relatively steady period when the outward pressure from fusion balances the inward pull of gravity. For a star like our Sun, this phase lasts about 10 billion years. But for a star as massive as Stephenson 2 to 18, the main sequence doesn't last long at all, just a few million years at most.
Why so short?
Because bigger stars burn through their nuclear fuel at a ferocious pace. Think of it like this: if the Sun is a modest campfire that can smolder quietly for a long night, Stephenson 2 to 18 is a roaring bonfire that blazes so intensely it consumes all its fuel in a flash. Massive stars are inefficient in terms of longevity. They trade stability for brilliance. After exhausting hydrogen in its core, Stephenson 2 to 18 would have begun fusing helium into heavier elements like carbon and oxygen. This transition is violent, causing the star's outer layers to expand enormously. That's how it ballooned into the red supergiant we see today. At this stage, the star's radius swelled to over 2,000 times that of the Sun, while its outer layers became cooler and puffier. What's happening inside is even more extreme. The core is layering up like an onion, with shells of fusion reactions stacked one atop another, hydrogen fusing outside helium, helium outside carbon, and so on. Each layer burns through its fuel more quickly than the last, as the star races toward its inevitable end. Stephenson 2 to 18 is firmly in this red supergiant phase. It has left behind the steady years of main sequence life and is now in the unstable, swollen period of late evolution. This stage doesn't last long, perhaps only a few 100,000 years, or even less. That might sound like a lot to us, but on cosmic timescales, it's like a candle sputtering before it goes out. The fact that we are alive in the tiny sliver of time when Stephenson 2 to 18 exists in this state is nothing short of remarkable. Inside, gravity is constantly battling against the incredible energy of fusion. Each time the core exhausts one fuel source, it contracts and heats up enough to ignite the next. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. That last step is critical. Fusion releases energy up to iron, but fusing iron actually consumes energy instead of releasing it. Once iron piles up in the core, the star has no way to generate the outward pressure needed to balance gravity. That's when the core collapses. So where exactly is Stephenson 2 to 18 in this chain? Based on its size, brightness, and temperature, astronomers believe it's currently fusing helium, possibly even carbon, in its core. That means it's somewhere in the late middle to advanced part of its red supergiant life. The exact stage is difficult to pin down because we can't peer directly into its core. But what we can say with confidence is that it's on borrowed time. In astronomical terms, Stephenson 2 to 18 is closer to the end than the beginning. It's sobering to think about. This is a star that likely formed around 15 to 20 million years ago, a blink of an eye compared to our Sun's 4.6 billion year lifespan. Already, it has lived through its main sequence, burned through vast reserves of hydrogen and helium, and swelled into one of the largest stars the universe has ever revealed to us. And sometime within the next million years, or possibly even sooner, it will meet its fate in a cataclysmic explosion. Massive stars like Stephenson 2 to 18 are rare jewels, and part of the reason is simply that they don't last long. Their very nature ensures they live spectacular but fleeting lives. Most of the stars we see in the night sky are smaller, longer-lived ones, because they have had billions of years to shine. The giant ones like Stephenson 2 to 18 are special because we're lucky enough to catch them during their short existence. Right now, Stephenson 2 to 18 is sitting at the most dramatic stage of stellar evolution. A swollen, glowing titan, its core working furiously to stave off collapse, its outer layers tenuous and unstable. It's the phase that comes right before the end, like the last movements of a symphony before the final crash of cymbals. It is, in many ways, a star living on cosmic borrowed time. The future of Stephenson 2 to 18 is written in fire, collapse, and unimaginable violence. Every massive star carries within it the seeds of its own destruction, and Stephenson 2 to 18, being one of the most bloated and extreme stars ever discovered, is heading straight for one of the most spectacular deaths in the universe, a supernova, or perhaps even a hypernova. As we left off, Stephenson 2 to 18 is in the red supergiant stage, its core working tirelessly to burn heavier and heavier elements in a desperate attempt to resist gravity. But this battle is unwinnable. Once fusion in its core eventually produces iron, the entire balance of the star tips. Unlike lighter elements, fusing iron doesn't release energy, it consumes it. The second that iron becomes dominant in the core, the outward pressure of radiation that has been holding the star's immense weight at bay vanishes. Gravity, relentless and unopposed, takes over. The result is sudden and catastrophic. The core collapses in just a fraction of a second, falling in on itself at a quarter of the speed of light. Temperatures soar into the billions of degrees. Protons and electrons smash together to form neutrons, releasing an unimaginably intense flood of neutrinos. Tiny particles that, in that instant, carry away more energy than all the stars in the universe combined are emitting. The collapsing core compresses into a ball just a few dozen kilometers across, either forming a neutron star or, if the mass is high enough, a black hole. At the same time, the outer layers of the star, those enormous, diffuse, fiery layers that once extended far beyond Saturn's orbit, suddenly lose the foundation beneath them. They slam into the rebounding core or are blasted outward by the shockwave driven by the neutrino flood. This is the supernova explosion, an event so bright that, for weeks or months, it can outshine an entire galaxy. To imagine that, billions of stars, and yet for a short time, Stephenson 218's death will radiate brighter than them all. But with a star as huge as Stephenson 2 to 18, the ending may not just be a supernova. Some astronomers suspect it could go further, a hypernova. A hypernova is an even more energetic explosion, releasing perhaps 10 times as much energy as a normal supernova. It's the kind of event thought to be linked with gamma-ray bursts, those terrifying beams of radiation that travel across the cosmos and can sterilize entire star systems if they're unlucky enough to be in the line of fire. Thankfully, Stephenson 2 to 18 is far enough away, around 19,000 light-years, that even if it does unleash such a blast, Earth will be completely safe. But the raw scale of such an explosion is something almost beyond human comprehension. Now, what will be left behind after this cosmic firestorm? That depends on the final mass of Stephenson 218's core. If it's just within the right range, the collapse will stall at the neutron star stage, leaving behind an object only about 20 kilometers wide, yet so dense that a single teaspoon would weigh billions of tons. But given Stephenson 218's extreme size and mass, the more likely outcome is that the core will collapse directly into a black hole. That means this once mighty star, which dwarfed everything in our solar system, will end its life as a dark, invisible singularity, an object so compact that not even light can escape. What's perhaps most astonishing is that this violent death is not the end of the story, but the beginning of something new. Supernovae and hypernovae are the great recyclers of the cosmos. When Stephenson 2 to 18 explodes, it will scatter its enriched elements, carbon, oxygen, silicon, iron, and even heavier elements, into the surrounding space. These are the building blocks of planets, moons, and even life. In fact, the iron in your blood, the calcium in your bones, and the oxygen in the air you're breathing right now all came from stars that died in supernovae billions of years ago. In a sense, Stephenson 218's death is part of a cosmic cycle of rebirth. One day, its remains could seed the formation of new stars, new planets, and perhaps even new life. For us, watching from afar, Stephenson 2-18 is both a marvel and a reminder. A marvel, because it shows us just how powerful the forces of nature can be. And a reminder, because it teaches us that even the largest, most seemingly eternal giants in the universe are mortal. Their lives are brief, their deaths violent, but in those deaths they ensure that the cosmos continues to evolve and thrive. So, the future of Stephenson 2-18 is not peaceful. It will not quietly fade away like our sun will billions of years from now. Instead, it will go out in a final act of defiance against gravity, a spectacular explosion that will ripple across the galaxy. When it does, it will mark the end of one of the biggest stars ever discovered, but also the beginning of new possibilities written into the fabric of the universe. When Stephenson 2-18 finally reaches the end of its colossal life and detonates in a supernova, or perhaps a hypernova, the scale of destruction and creation that follows will be staggering. To try and imagine the impact of its explosion is to stretch human imagination to its breaking point, because we're not just talking about something big in human terms. We're talking about an event so powerful it briefly rewrites the dynamics of an entire region of the galaxy. First, let's set the scene. When Stephenson 2-18 collapses, the core will implode and rebound in less than a second, sending shockwaves roaring outward. In an instant, the star's outer layers, so large that they could engulf Saturn's orbit if Stephenson the 18th of February Saturday in the center of our solar system, will be ripped away at speeds of thousands of kilometers per second. That's fast enough to cross the distance from Earth to the Moon in less than a minute. The result is a supernova blast wave expanding into the surrounding interstellar medium with the force of 10 to the power of 44 joules of energy. To put that in perspective, that's more energy released in a few seconds than our sun will emit in its entire 10 billion year lifespan. Now, the immediate region around Stephenson 2-18 will be utterly transformed. Any nearby planets, moons, or smaller stars will be vaporized. Even gas clouds light years away will feel the shock, compressed and energized by the blast. This compression can actually trigger the birth of new stars by forcing clouds of hydrogen to collapse, meaning that Stephenson 2-18's death will literally seed the next generation of stellar life. The light from the explosion itself will be astonishing. For weeks or months, the supernova will shine with the brilliance of billions of suns. If Stephenson 2-18 were closer to Earth, say, within just a few thousand light-years, it would blaze so brightly in our sky that it would outshine the full moon and even cast shadows at night. Thankfully, at 19,000 light-years away, the Earth is safe from its destructive effects. Still, when it goes, it will likely be visible with the naked eye from Earth, appearing as a new star in the constellation Scutum, a jewel glowing brilliantly in our night sky. But brightness is only part of the story. The explosion will flood space with radiation, X-rays, gamma rays, and neutrinos. Gamma rays, in particular, are dangerous, because if a hypernova unleashes a gamma ray burst in our direction, it could devastate planetary atmospheres even thousands of light-years away. Fortunately, Stephenson 2-18's orientation and its distance mean Earth is not in the line of fire. But closer systems may not be so lucky. This is why gamma-ray bursts are considered some of the deadliest natural events in the cosmos. Cosmic sniper shots capable of sterilizing entire regions of space. Then comes the material expelled into the galaxy. The explosion will eject vast amounts of heavy elements into its surroundings. We're talking about millions of Earth masses worth of oxygen, silicon, calcium, and iron, along with trace amounts of gold, uranium, and other precious metals. Everything heavier than iron that will scatter across space in the wake of Stephenson 2-18's death can only be created in these extreme conditions. It is through such violent ends that the universe becomes enriched, allowing planets like Earth and beings like us to exist. Without stars like Stephenson 2-18 going supernova, the cosmos would be nothing but hydrogen and helium, a barren expanse devoid of complexity. On a more local galactic scale, the shockwaves from the explosion could help shape the structure of the Milky Way. Supernova remnants expand for tens of thousands of years, carving out cavities, heating interstellar gas, and weaving turbulence into the galactic environment. These structures, which astronomers can observe even millions of years after the initial blast, are often some of the most beautiful sights in the universe. Glowing nebulae formed from the shreds of a once great star. The Crab Nebula, for instance, is a famous remnant of a supernova that exploded in 1054 AD, and yet, it still glows brightly in telescopes today. Someday, Astronomers may look at the remnant of Stephenson 218's death and marvel at its beauty, knowing that it is both the grave of a giant and the cradle of new worlds. The gravitational aftermath is no less profound. Depending on the final mass of its core, Stephenson 218 will either leave behind a neutron star or, more likely, collapse into a black hole. If it does become a black hole, it will be one of the most massive stellar black holes ever born, an invisible scar on spacetime marking where a titan once burned. This black hole could eventually merge with others, creating gravitational waves, ripples in the fabric of space itself, that astronomers on Earth may someday detect. And yet, for all this chaos, for all this unimaginable destruction, the supernova of Stephenson 218 is ultimately about creation and balance. Its explosion will scatter matter that may someday become new stars, new solar systems, and perhaps even new forms of life. Its death will contribute to the ongoing evolution of the Milky Way, just as the deaths of earlier stars billions of years ago made our existence possible. It is, in the most literal sense, both an ending and a beginning. So, when Stephenson 218 finally blows apart, it will be one of the most spectacular shows in the galaxy, a titanic event that astronomers may be able to observe from Earth for years. But more than that, it will be a cosmic reset button, turning one giant star into the seeds of countless future stars and worlds. And while we may feel or fear at the raw scale of such an event, we should also feel gratitude, for without supernovae like this, we would not be here to wonder about them at all. Betelgeuse is probably the most famous red supergiant in the night sky. It shines brightly in the constellation Orion, marking the hunter's shoulder with a distinct reddish hue. For centuries, it has captured human imagination. Ancient cultures looked at it as the fiery heart of Orion, a star so large and so bright that it almost felt alive. In recent years, Betelgeuse has fascinated astronomers and the public alike because of its sudden dimming episodes, sparking worldwide speculation that it might be on the verge of going supernova. And yet, for all of its notoriety and its gargantuan size compared to our Sun, when you set Betelgeuse next to Stephenson 218, it suddenly looks small. Let's put this in perspective. Betelgeuse is massive. Its radius is about 764 times that of the Sun on average. That's already beyond comprehension. If Betelgeuse were placed at the center of our solar system, it would extend past the orbit of Mars and possibly swallow up Jupiter's orbit depending on how you measure its variable size. For years, astronomers regarded Betelgeuse as one of the largest known stars, a true colossus. But then along came Stephenson 218, and it completely redefined the meaning of big. Stephenson 218's radius is about 2,150 times that of the Sun. That means it is nearly 3 times larger than Betelgeuse in sheer radius. But remember, volume doesn't scale linearly with radius, it scales cubically. When you compare the volumes of these two red supergiants, Stephenson 218 is not just 3 times larger, it's over 30 times the volume of Betelgeuse. 30. That means you could fit dozens of Betelgeuses inside Stephenson 218's vast stellar envelope. To make this comparison more visual, picture Betelgeuse as a massive beach ball. Now imagine Stephenson 218 not as a slightly larger ball, but as an entire stadium dome. Betelgeuse would float inside it like a toy. This is how wildly different their scales are. And yet, it's almost unfair to diminish Betelgeuse in this way, because Betelgeuse itself is still a monster compared to nearly every other star in our galaxy. The Sun, for example, could be swallowed up millions of times over by Betelgeuse's volume. The fact that even such a legendary star pales in comparison to Stephenson 218 tells us just how extreme Stephenson really is. It is the outlier among outliers, the giant among giants. Another difference worth mentioning is visibility. Betelgeuse is a household name among stargazers because we can see it directly with the naked eye. It's only about 642 light-years away, relatively close by cosmic standards, and shines as one of the brightest stars in the night sky. Its reddish glow is unmistakable, and because of its proximity, it's one of the most studied stars in the universe. Stephenson 218, on the other hand, is buried deep in the dust of the Milky Way, nearly 19,000 light-years away, invisible to the unaided eye. It requires sophisticated infrared observations to even glimpse it. In other words, Betelgeuse is the celebrity superstar of the sky, while Stephenson 2-18 is the elusive titan, hidden in shadows but vastly more powerful. Betelgeuse and Stephenson 2-18 also represent different chapters in the life of red supergiants. Betelgeuse is thought to be relatively close to the end of its life. Its irregular dimming events suggest it's shedding mass and behaving in ways typical of a star nearing its supernova finale. When Betelgeuse does eventually explode, it will be visible from Earth even in the daytime sky, a historic cosmic spectacle for humanity. Stephenson 2-18, while also in its red supergiant phase, is larger and will end even more violently, probably as a hypernova, and its death will scatter far more matter into the galaxy. But because it is so distant, its explosion won't be the awe-inspiring show Betelgeuse's will be from Earth's perspective. This contrast is fascinating. The star that looks biggest to us in the sky, Betelgeuse, is not the biggest by any physical measure, it just happens to be closer. Meanwhile, the true king, Stephenson 2-18, lurks far away, hidden from casual stargazers but unrivaled in its sheer size. If Betelgeuse is the star we can admire with our eyes, Stephenson 2-18 is the one that humbles astronomers with its enormity. So, when people ask about the largest star they can see with the naked eye, the answer is Betelgeuse. But when they ask about the largest star we know exists, the crown belongs to Stephenson 2-18. The two stand as symbols of scale, one within our grasp, the other beyond our imagination. And in this comparison, Betelgeuse, once considered immense, becomes a reminder that there are always bigger giants out there waiting to be discovered. VY Canis Majoris is another titan that once held the throne as the largest known star. For many years, astronomy textbooks and popular science documentaries celebrated it as the ultimate giant, the very limit of how large a star could become. Nestled in the constellation Canis Major, about 3,900 light-years from Earth, VY Canis Majoris was considered the gold standard of stellar enormity. And to be fair, it truly is enormous. It's a red hypergiant, one of the most luminous and massive of its kind. But when Stephenson 2-18 entered the scene, it became clear that even this celebrated giant wasn't the ultimate champion. So how big is VY Canis Majoris? Its radius is estimated to be around 1,420 times the radius of the Sun. That's mind-bending on its own. If you were to replace the Sun with VY Canis Majoris, its outer layers would stretch past the orbit of Jupiter and nearly to Saturn. That means it could swallow the first 5 planets of our solar system whole, with room to spare. For a long time, this was the very definition of unimaginably large. But then, astronomers began refining their techniques, measuring distances more accurately, and reanalyzing old data. It turned out that VY Canis Majoris, while still massive, wasn't as big as some earlier estimates suggested. Meanwhile, stars like UY Scuti and eventually Stephenson 2-18 were revealed to be even larger. Stephenson 2-18, with its radius of about 2,150 solar radii, completely dwarfs VY Canis Majoris. That means Stephenson 2-18 is about 1.5 times larger in radius than VY Canis Majoris, but when you factor in volume, the difference grows exponentially. The volume of Stephenson 2-18 is nearly 4 times that of VY Canis Majoris. So while VY Canis Majoris is no small player, it now looks like a younger sibling trying to measure up to an older brother of cosmic proportions. But the story of VY Canis Majoris is still fascinating. Unlike Stephenson 2-18, VY Canis Majoris is a red hypergiant, a classification reserved for stars even more unstable and extreme than red supergiants. Its outer layers are constantly being shed into space, creating vast clouds of gas and dust that surround it. These ejector clouds are so huge that telescopes have imaged them as sprawling arcs and knots extending thousands of astronomical units from the star. It is literally tearing itself apart before our eyes, a star in the process of self-destruction. In this sense, VY Canis Majoris is a more dramatic and chaotic object than Stephenson 2-18, even if it's smaller in size. When we line them all up, Betelgeuse, VY Canis Majoris, UY Scuti, and Stephenson 2-18, a clear ranking emerges. Betelgeuse is the smallest of the group, though still a massive red supergiant compared to ordinary stars. VY Canis Majoris sits above it, a red hypergiant with a size that could consume most of our solar system. UY Scuti was once considered the king, with a radius around 1,700 times that of the Sun, making it larger than both Betelgeuse and VY Canis Majoris. But then comes Stephenson 2-18, the undisputed monarch, surpassing them all with a radius of 2,150 suns. It's like comparing mountains. Betelgeuse is Everest, VY Canis Majoris is K2, UY Scuti is Kanchenjunga, and Stephenson 2-18 is Olympus Mons, standing so far above the rest that it redefines the entire category. What's especially interesting here is how these stars shift in ranking over time. Measurements improve, and once touted champions get dethroned. VY Canis Majoris is a great example of this. Decades ago, some estimates placed it as big as 3,000 solar radii, making it seem larger than Stephenson 2-18. But those early calculations relied on less precise data, and as astronomers revisited it with better technology, they discovered it wasn't quite as monstrous as originally thought. This doesn't diminish its importance. It remains one of the most extreme stars we've ever studied, but it does highlight how fluid our knowledge of the cosmos can be. One could also say that VY Canis Majoris and Stephenson 2-18 embody different aspects of stellar extremity. VY Canis Majoris is a chaotic, unstable furnace, rapidly losing mass and cloaking itself in dusty shells as it spirals toward death. Stephenson 2-18, by contrast, is less chaotic but far larger in size, a calm leviathan that silently dominates in sheer bulk. Both are extraordinary, but in different ways. So when astronomers now list the largest known stars, the ranking puts VY Canis Majoris below both UY Scuti and Stephenson 2-18. Betelgeuse, despite its fame, doesn't even make it close to the top. And Stephenson 2-18? It sits comfortably at number 1, the reigning king of stellar giants, reminding us that for every extreme object we know, there may always be something even bigger, even stranger, lurking in the shadows of our galaxy, waiting to be discovered. Here's where things get especially interesting, and maybe even counterintuitive. When most people hear that Stephenson 2-18 is the largest star in the universe, they immediately assume it must also be the most massive. After all, doesn't size directly translate to mass? It seems like common sense. The bigger something is, the heavier it should be. But in the world of stars, the reality is far stranger. Stephenson 2-18 is indeed the largest star in terms of radius and volume, but it is not the heaviest star we know of. In fact, when it comes to mass, it doesn't even come close to holding the crown. To understand this, think about the difference between a soap bubble and a bowling ball. The soap bubble might look huge compared to the small, dense bowling ball, but it barely weighs anything in comparison. Stephenson 2-18 is the cosmic soap bubble. Its outer layers are spread out across an enormous volume, giving it that staggering size, but those layers are extremely tenuous, so thin and diffuse that they're almost like a cosmic fog. That's why, despite having a diameter that could engulf Saturn's orbit, it's not anywhere near the most massive star out there. Stephenson 2-18 is estimated to have a mass of about 30 to 40 times the mass of the Sun. Now, that's still huge compared to our Sun, which is only one solar mass by definition. But when you compare it to stars like a 136A1 in the Tarantula Nebula, the difference is shocking. Our 136A1, for example, is one of the most massive stars ever found, weighing in at over 200 times the mass of the Sun. That's more than 5 times the mass of Stephenson 2-18. But here's the kicker, our 136A1 is only about 30 times the radius of the Sun, which makes it look puny compared to the giant red supergiants. So you have this small but super heavy star versus this massive but lightweight giant. This is why astronomers distinguish carefully between largest and most massive. They are not the same. Stars like our 136A1 are extremely compact and incredibly dense, burning furiously with surface temperatures reaching over 40,000 Kelvin. They shine with a brilliance millions of times greater than the Sun, but because they are so hot and their energy output is so extreme, they cannot afford to puff up like a red supergiant. Instead, their immense gravity keeps them relatively compact. Stephenson 2-18, on the other hand, has bloated to a colossal size because of where it is in its stellar life cycle, its outer layers expanding outward while the core process is slow. So in terms of rankings, Stephenson 2-18 is number 1 in sheer size and volume, but it doesn't even rank near the top in mass. It's a bloated giant, a star that has reached maximum puffiness but not maximum weight. Think of it as the biggest balloon in the universe. It fills the most space, but but it's mostly emptiness compared to the compact, supermassive stars that burn hot and fast elsewhere in the galaxy. This distinction also helps explain why Stephenson 2-18 has a relatively low density compared to smaller, more massive stars. Its gravity isn't strong enough to keep its outer layers tightly packed. Instead, those layers are drifting far away from the core, giving the star its bloated appearance but also lowering its overall density. It's like comparing a sponge to a rock. The sponge might be bigger, but the rock packs more material into a smaller space. Another way to think of it is this: if you tried to put Stephenson 2-18 on a cosmic weighing scale next to a true heavyweight like a 136A1, Stephenson 2-18 would tower over it in size, but the scale would tip heavily toward a 136A1. Stephenson 2-18 wins the prize for volume, but loses in the mass category. This difference between mass and size is crucial in astrophysics because it determines how stars evolve and how they die. More massive stars burn their fuel far more quickly, living short but spectacular lives before collapsing into black holes. Larger stars like Stephenson 2-18, while still massive compared to the Sun, burn less furiously and bloat outward during the red supergiant phase, setting themselves up for a slightly different fate. Both are extreme in their own way, but their differences highlight the diversity of how stars can push the boundaries of physics. So while it's tempting to say Stephenson 2-18 is the biggest and the baddest of all stars, the truth is more nuanced. It is the undisputed champion in terms of physical size, but when it comes to mass, it bows down to stars like a 136A1 and other ultramassive blue giants that may never expand to such enormous radii. Bigger doesn't always mean heavier, and in the universe, it's the contrast between size and mass that makes stars like Stephenson 2-18 so fascinating. When we look at Stephenson 2-18 and marvel at its sheer size, it's easy to imagine it as an unimaginably heavy, solid, crushing behemoth, like some kind of celestial iron ball taking up half the solar system. But the truth couldn't be more different. Stars of this scale, especially red supergiants like Stephenson 2-18, are shockingly not dense at all. In fact, they're some of the fluffiest, least dense objects in the known universe, with outer layers so tenuous and spread out that they're more like cosmic fog than solid matter. To understand this, let's zoom into the structure of such a star. At the core of Stephenson 2-18, deep down where nuclear fusion is happening, the material is incredibly dense and hot. That's the furnace where hydrogen and helium are being fused into heavier elements. But the farther you move outward from the core, the less dense the material becomes. By the time you reach the outer layers, the gas is spread so thinly that if you could somehow scoop up a chunk of the star's atmosphere and bring it to Earth, it might be less dense than the air we're breathing right now. That's how bizarrely diffuse these giants are. Let's put this into perspective. Density is just mass divided by volume. The Sun, our familiar yellow star, has an average density of about 1.4 grams per cubic centimeter, a little denser than water. That means if you could somehow put the Sun in a giant cosmic swimming pool, it would actually sink, because water has a density of 1 gram per cubic centimeter. Now, compare that to Stephenson 2-18. Its mass is maybe 30 to 40 times that of the Sun, but its volume is over 10 billion times larger. When you divide mass by volume, the average density you get is staggeringly low, around a few 10,000ths of a gram per cubic centimeter. In other words, the average density of Stephenson 2-18 is less than that of styrofoam. Some estimates even suggest its outer layers approach densities comparable to Earth's atmosphere at high altitudes. Imagine that for a second, the largest star in the known universe is, in a sense, lighter than a packing peanut. If you could somehow stand inside the outer atmosphere of Stephenson 2-18, it might not even feel solid. It would feel like a tenuous, glowing mist surrounding you on all sides. That's what makes red supergiants so visually breathtaking and yet so fragile. They're not tightly bound objects like neutron stars or white dwarfs. They're bloated balloons of plasma, barely held together by their own gravity. This fluffiness is also one of the reasons why stars like Stephenson 2-18 lose mass so easily. Their gravity isn't strong enough to hold onto those distant outer layers with much force. A gentle push from stellar winds or radiation pressure can send entire streams of gas flowing away into space. Over time, these stars shed a significant portion of their mass, creating glowing nebulae and seeding the galaxy with heavy elements that will one day form new stars, planets, and even life. In fact, This mass loss is part of why these stars eventually explode as supernovae. They can't hold their structures stable forever. Another fascinating consequence of this low density is how it changes our perspective on what big really means. Stephenson 2-18 may be the largest star in terms of physical radius, but much of that size is just empty space filled with tenuous plasma. If you compared it to something like a neutron star, which packs more mass than the Sun into a sphere just 20 kilometers wide, the contrast is almost comical. The neutron star would be unimaginably small in size compared to Stephenson 2-18, but a trillion times denser. 1 teaspoon of neutron star material would outweigh entire mountains on Earth, while a teaspoon of material from the outer atmosphere of Stephenson 2-18 might weigh less than a feather. So, in a way, Stephenson 2-18 is like the illusion of bigness. It takes up more space than anything we know, but the actual substance is surprisingly thin. That's what makes its physics so intriguing. It's a constant balancing act between the pull of gravity and the push of radiation pressure. The star is puffed up to this colossal size precisely because its outer layers are so diffuse and weakly bound. If they were any denser, the star wouldn't be nearly as large. This leads us to another mind-bending idea. If you were somehow to travel across the diameter of Stephenson 2-18, you wouldn't be plowing through dense, crushing matter. Instead, you'd drift through layer upon layer of gas so spread out that it might not feel much different than drifting through a thin nebula in space. It's less like swimming through water and more like floating through a glowing fog that just happens to extend for billions of kilometers. So the lesson here is that size doesn't always mean density, and density doesn't always mean mass. The largest star in the universe is, paradoxically, also one of the least dense types of stars. It is vast, it is awe-inspiring, but it is also delicate, fragile, and ethereal, more like a glowing cosmic cloud than a solid sphere of fire. And that fragility is exactly what ensures its eventual collapse, because stars this puffed up cannot remain stable for long. If you could ride a beam of light like a cosmic racetrack, Stephenson 2-18 would be the longest lap you'd ever take around a star. Start with the basic geometry. A sphere's track at its equator is its circumference, 2r. For Stephenson 2-18, the radius is about 2,150 times the Sun's. The Sun's radius is roughly 696,340 kilometers, so multiply 2,150 times 696,340 almost equals 1,497,131,000 kilometers. That's the radius, not the diameter. Now wrap a tape measure around that swollen equator. 2 are almost equal to 2 times 3.14159 times 1.497 times 10 kilometer almost equal to 9.41 billion kilometers. That single number is outrageous by itself. A racetrack more than 9 billion kilometers long, not around a galaxy, not around a nebula, around one star. Light is the universe's speed limit, tearing along at about 299,792 kilometers per second in a vacuum. Divide distance by speed to find the lap time. 9.41 times 10 kilometer divided by 299,792 kilometers per second almost equal to 31,378 seconds, which is about 8 hours 43 minutes. Yes, light would have time to clock a full workday with a lunch break just to get around the rim of this star once. By comparison, light can whip around the Sun in roughly 14.6 seconds. That means a single Stephenson-sized lap takes over 2,000 times longer than a lap around our Sun. If the Sun is a quick sprint around the block, Stephenson 2-18 is an overnight ultramarathon through cosmic fog. To ground that even more, let's stack up a few intuitive yardsticks. The Earth's entire equatorial circumference is about 40,075 kilometers. Light races around Earth in roughly 0.13 seconds, literally the blink of an eye. Around the Sun, as we said, it needs a quarter of a minute. Around Stephenson 2-18, light is busy for almost 9 hours. If a photon began its lap at 9 o'clock in the morning, you wouldn't see it cross the finish line until nearly 6 p.m. in an Earth day. If you're more of a night owl, imagine releasing that photon at midnight. It doesn't get back to you until breakfast time. Because measurements of such diffuse giants carry uncertainties, it's fair to consider a realistic range. If Stephenson 2-18 were on the slightly smaller side, say 2,000 solar radii, the lap time drops to about 8.1 hours. On the larger side, 2,400 solar radii, it stretches to almost 9.7 hours. In other words, no matter where the exact radius lands within reasonable estimates, the light lap stays in the neighborhood of a full workday. That constancy of scale is part of what makes the star's immensity sink in. Whether you shave off an hour or add one, you're still nowhere near the sun's 14-second breeze. It's tempting to ask why the lap is so long when the surface temperature is relatively cool, 200 K. Temperature, however, isn't what sets the lap time, geometry does. A cooler photosphere simply means each square meter of surface emits less energy than a hotter star's. But Stephenson 2-18 multiplies that modest per meter flux by an absurd number of square meters. The circumference, and therefore the lap of light, scales straight with radius, and the surface area scales with the square of radius. So this star doesn't win because it's hotter. It wins because it's everywhere. The racetrack is so long that even light has to respect the clock. Try a different angle. Communication delay. Suppose a spacecraft skims the photosphere at the equator and tries to ping a receiver half a world away along that rim. On Earth, a signal skirting the equator to the opposite side would be there in less than 1/10 of a second. On the Sun, it's a handful of seconds. On Stephenson 2-18, that side-to-side message, hugging the surface, takes about 4 hours 20 minutes, half the circumference's light time. So a hello whispered around the rim doesn't just echo, it lingers. You could send a note at lunchtime and get the reply at dinner. Or imagine a photon relay. You post a series of mirrors just above the star's limb, each one catching and handing off a light pulse along the equator. The handoff intervals would tick like the hours on a clock, this mirror to the next, until the pulse finally returns to its starting mirror. A solar relay would finish while you count to 15. A Stephenson relay would be the length of a long-haul flight. And speaking of flights, humans love speed metaphors. The International Space Station orbits Earth at 7.7 km/s, finishing a lap in about 90 minutes. Scale that up to Stephenson 2-18. At ISS speed, a single equatorial circuit would take over 38 years. A fast airliner at 900 km/h could loop the Sun in about 202 days, if it could survive, which it couldn't, but it would need over 1.2 million years to drive the Stephenson track at that same speed. Even the Parker Solar Probe, the fastest human-made object, topping 190 km/s near perihelion, would need over 1.5 years to grind out the 9.4 billion kilometer loop. The numbers pile up relentlessly, and that's the point. In stellar geometry, Stephenson 2-18 is where intuition goes to drown. Another way to view it is in terms of day-night rhythm. Around the Sun, a photon's day, one lap, is a coffee break. Around Stephenson 2-18, it's a full shift. That has a subtle psychological punch. Light, which we think of as instantaneous, is forced to move at human timescales by mere distance. We're not slowing light down. We've just built a track so impossibly long that the ultimate sprinter looks patient. What about the shortest path caveat? Strictly, the quickest point-to-point route from A to B on a sphere is a great circle, and around the equator, that's exactly what we're using. If you allowed the photon to leave the surface and cut a chord through the star's interior, it wouldn't help. Stars aren't transparent at optical wavelengths, and inside, photons random walk, scattering again and again. In a star's interior, the effective speed of light is dragged into absurdly long diffusion times. It takes thousands to hundreds of thousands of years for a photon created in the sun's core to wander out. So if you want a crisp, ballistic lap, you stick to the vacuum just above the photosphere, the equatorial highway we've been timing. Spin adds another wrinkle. Red supergiants often rotate slowly compared to compact stars, but any equatorial bulge from rotation slightly changes the circumference. For Stephenson 2-18, the effect is likely minor relative to its overall size and the broad uncertainties in measuring its edge, which is a fuzzy, convective photosphere rather than a crisp boundary. Think of our number, 8.7 hours, as a beautifully instructive estimate, rather than an immutable constant. Push the radius up or down by a few percent and you slide the lap time by tens of minutes, not orders of magnitude. While we're calibrating intuition, compare the lap time to the scale of the solar system. Pluto's average orbital radius is about 5.9 billion kilometers. Stephenson 2-18's equatorial loop is 1.5 times Pluto's orbital distance. That's how you get to hours for light. You've essentially wrapped a racetrack longer than the outer solar system around a single star's waist. And all of this is happening at the surface of an object whose outer layers are so diffused they're closer to a luminous fog than a solid shell. That's the final twist of the knife. The lap is long not just because the radius is big, but because most of what defines that radius is whisper-thin plasma tenuously held by gravity and puffed up by radiation and convection. You're racing along the edge of a cloud that glows, and the cloud is so gargantuan that speed itself bows to scale. It's worth acknowledging one more subtlety. The values we've used, 2,150 solar radii, 3,200 K surface temperature, are derived from models plus observations corrected for distance and dust. If subsequent measurements nudge the radius, the light lap follows proportionally. Shrink the radius by 5%, shrink the lap by 5%. Grow the radius by 10%, and you add close to an hour. Within reasonable bounds, though, the narrative doesn't change. Light, fast, unforgiving light, needs hours to circle Stephenson 2-18. That single fact condenses the star's immensity into a stopwatch you can hold in your mind. So when someone asks, how big is the biggest star? One answer is to hand them a clock. Set it to midnight as the photon leaves your fingertip above the equator. Come back near 8 hours and 43 minutes to watch it return. The gap between those two moments, that long, human-sized stretch of time, is the measure of a star that turns numbers into awe. It feels like a trick of the universe, doesn't it? Here we are talking about the single largest known star in existence, a behemoth so gargantuan that light takes nearly 9 hours just to travel around its equator, and yet if you walked outside on a clear night, tilted your head back, and swept your gaze across the heavens, you would not see it. Stephenson 2-18, despite being one of the most extreme objects ever discovered, is completely invisible to the naked eye. And that raises a very natural question. How can something so enormous, so luminous, so outrageously oversized, remain hidden from us? The answer lies in three overlapping truths: distance, dust, and the quirks of human eyesight. Let's start with the most obvious culprit: distance. Stephenson 2-18 resides about 19,000 light-years away in the constellation Scutum. That's an immense gulf by stellar standards. For perspective, Betelgeuse, another giant red supergiant that often grabs headlines, is only about 640 light-years away. Rigel, the brilliant blue supergiant in Orion, glows at a distance of about 860 light-years. Even Deneb, one of the most distant stars you can still see with the naked eye, sits around 2,600 light-years away, which is already pushing the boundaries of unaided visibility. Stephenson 2-18 is almost 10 times farther than that. Light leaving its surface today won't reach our eyes until the year 21,025, and in that journey it has to survive passage through vast interstellar clouds and dimming effects that strip away its brilliance. In short, distance alone ensures that much of its luminosity is diluted before it ever reaches Earth. But distance is only part of the story. The second reason is arguably even more important: dust. Stephenson 2-18 is located deep in the galactic plane, inside the Stephenson 2 cluster, which itself is shrouded in dense clouds of interstellar dust and gas. This dust behaves like a cosmic fog, scattering and absorbing visible light before it can travel freely. What does make it through is dimmed and reddened, a process astronomers call interstellar extinction. Imagine driving at night through heavy fog with your headlights on. The beams are still incredibly bright at the source, but by the time they reach your eyes, the glow is muffled and blurred into obscurity. That's exactly what happens with Stephenson 2-18. Its light is not absent, it's simply muted, smothered by a veil of dust particles stretched across thousands of light-years of galactic medium. Astronomers can still detect it using infrared wavelengths, because infrared light pierces through dust far more efficiently than visible light. But to the naked eye, our atmosphere and eyes are tuned for visible light, leaving the star hidden from view. The third factor is our own biological limitation. Human eyes are surprisingly capable for creatures evolved to navigate Earth's surface, but they are woefully inadequate for probing the depths of interstellar space. The faintest stars we can see under pristine, pitch-black conditions are about magnitude +6 on the apparent brightness scale. Anything fainter requires binoculars, a telescope, or special imaging equipment. Astronomers estimate that if there were no dust in the way, Stephenson 2-18 would shine around magnitude +7 or brighter, close to the edge of human detection but still faint compared to the bright dots we're used to seeing. With the dust factored in, its apparent brightness falls well below the naked eye threshold. In other words, the star could be burning with tens of thousands of times the luminosity of the sun, but our eyes are simply blind to it because of how much intervening space dulls its glow. To make this even more concrete, compare it to Betelgeuse. Betelgeuse is enormous, yes, but nowhere near the scale of Stephenson 2-18. And yet Betelgeuse shines brightly in our winter skies, unmistakable with its reddish hue. The difference is that Betelgeuse is close, unobscured, and lucky enough to sit in a relatively dust-free window of the sky. Stephenson 2-18 is unlucky in all three respects: far away, heavily dust-obscured, and buried in one of the densest parts of the Milky Way's plane. It's like standing in a crowded, smoky concert hall. Your friend on stage might be strumming the loudest guitar in the room, but if you're too far back and there are too many bodies between you, all you'll hear is a faint echo. Now, there's a poetic irony here. Stephenson 2-18 is one of the brightest stars in the Milky Way by intrinsic luminosity, perhaps 440,000 times brighter than our Sun, yet it hides in anonymity, invisible to us unless aided by the instruments of science. It is the cosmic equivalent of a giant living in a distant land, shouting at full volume, but whose voice we can't hear because the wind and distance swallow the sound. This should remind us that what we see with our own eyes is only a fraction of the universe's true theater. The night sky, dazzling though it appears, is like a censored version of reality, edited down by distance, by interstellar smog, and by the limits of human biology. The real show lies beyond what we can see unaided. This invisibility also explains why it took modern astronomy to even identify Stephenson 2-18 in the first place. Ancient skywatchers mapped the heavens meticulously, naming stars, forming constellations, and passing stories through generations. But Stephenson 2-18 left no mark in myth, no record in the lore of civilizations, because to the human eye it simply wasn't there. It waited in the shadows until astronomers armed with infrared-sensitive instruments and modern telescopes could reveal it. And in this sense, its invisibility becomes part of its mystique. Unlike Sirius or Betelgeuse or Polaris, Stephenson 2-18 isn't a star you can point at in the night sky. It's a discovery you meet only through science, not through sight. So the next time you gaze upward and marvel at Orion's belt, at Vega, at the shimmering river of the Milky Way stretching overhead, remember that lurking beyond your vision are titans greater than anything visible. Giants like Stephenson 2-18, cloaked in distance and dust, whispering their existence not to your eyes, but to the patient instruments of astronomy. And perhaps that's fitting. Some wonders of the cosmos are meant to dazzle us directly. Others, like Stephenson 2-18, challenge us to push beyond natural limits, to invent tools that let us pierce the veils of darkness and see what the naked eye cannot. If Stephenson 2-18 teaches us anything, it's that the universe does not give up its secrets easily. You might think that measuring the size of a star is as simple as pointing a telescope at it and calculating how big it looks. But when we're dealing with objects nearly 19,000 light-years away, hidden in dusty regions of the Milky Way, and bloated to such extraordinary scales, the process becomes one of the most difficult puzzles in astronomy. And this is why estimates of Stephenson 2-18 size, around 2,150 times the radius of our Sun, come with caveats and ranges rather than pinpoint precision. Measuring such extremes is as much art as it is science. The first difficulty comes from distance itself. Everything in astronomy depends on knowing how far away something is. If you don't know the distance, you can't know its true size or luminosity, you can only guess. For stars relatively close to us, astronomers use a technique called parallax, which measures the apparent shift in a star's position as Earth orbits the Sun. It works beautifully for stars a few hundred or even a few thousand light-years away. But for Stephenson 2-18, sitting at nearly 19,000 light-years, the parallax shift is so tiny that it's nearly impossible to detect with traditional ground-based observations. Even with advanced missions like Gaia, which has given us the most precise star maps ever created, the uncertainties are significant at such distances, especially when dust obscures the view. And if the distance is uncertain, the calculated size automatically inherits that uncertainty. A small error in distance translates into a huge difference in the estimated radius of the star. Next comes the issue of dust and extinction. As we discussed earlier, Stephenson 2-18 lies in one of the dustiest regions of the galaxy. This dust scatters and absorbs light, especially in the visible spectrum, which makes the star look dimmer and redder than it really is. To correct for this, astronomers have to estimate how much light is being blocked. But the dust itself isn't uniform. It's patchy, clumpy, and varies along different lines of sight. Think of it like trying to measure the brightness of a lighthouse while looking through shifting fog banks. You can guess how much the fog dims the light, but you'll never be perfectly certain. And because luminosity is directly tied to the estimated radius of the star, dust introduces yet another major uncertainty. Then there's the problem of defining the edge of the star. Unlike a planet, which has a solid surface, stars are made entirely of plasma. Their outer layers don't end abruptly, they just get thinner and thinner until they fade into space. In a star like Stephenson 2-18, those outer layers are so diffuse that they resemble a haze rather than a boundary. So where do you draw the line and say, this is the radius? Astronomers usually define a star's radius based on where the atmosphere becomes opaque to a specific wavelength of light. But that's a bit like trying to define the size of a campfire by asking where the smoke stops being visible. It depends on how you look at it and what tools you use. Different wavelengths of observation, visible, infrared, or radio, can give slightly different answers for the star's apparent size. Another complication arises from the irregularities of red supergiants. These stars aren't stable, smooth spheres. They have giant convection cells on their surfaces, hot bubbles of plasma rising and falling, sometimes spanning hundreds of millions of kilometers. This gives their photospheres, the visible surface, a mottled, uneven appearance. Betelgeuse, for example, has been observed to change brightness dramatically due to these surface variations and massive dust outflows. For a star as massive and bloated as Stephenson 2-18, such turbulence is almost certainly happening, which means its size isn't a fixed, well-defined number. The outer layers expand and contract, flare and dim, making its true boundary a moving target. Astronomers also face challenges with instrumentation and resolution. At such distances, Stephenson 2-18 appears as nothing more than a point of light through most telescopes. We can't see its disk directly the way we can for Betelgeuse, which is closer and has been imaged as a resolved star. Instead, scientists must rely on indirect methods, measuring its spectrum, analyzing its brightness across multiple wavelengths, and using models of stellar atmospheres to estimate its radius. These models, while sophisticated, are still approximations. They depend on assumptions about how energy is transported through the star, how much dust lies between us and the star, and what its temperature is, all of which come with uncertainties. Speaking of temperature, that introduces yet another layer of difficulty. The radius of a star is often calculated using the Stefan-Boltzmann law, which relates luminosity, temperature, and radius. If you know two of those variables, you can solve for the third. But measuring the surface temperature of a red supergiant is notoriously tricky. Their spectra are filled with molecular absorption bands, and the outer layers don't radiate like a clean blackbody. A difference of just a few hundred Kelvin in the temperature estimate can swing the radius calculation by hundreds of solar radii. For Stephenson 2-18, that could mean the difference between it being merely extremely large or record-shatteringly gigantic. Finally, there's the problem of stellar variability over time. Stars like Stephenson 2-18 aren't static objects. They pulsate, they lose mass, and their brightness can fluctuate. Over decades of observation, it's possible that the star's radius has changed slightly, making the task of pinning down a single size even more complicated. We're essentially trying to measure a moving target cloaked in fog from nearly 20,000 light-years away. So when astronomers say that Stephenson 2-18 is about 2,150 times the radius of the Sun, it's best to think of that as an approximation rather than an exact measurement. The real value might be slightly smaller or even larger, depending on which assumptions you make. The fact that we can even estimate such a number, given the challenges, is a triumph of modern astronomy. But it's also a humbling reminder of how much uncertainty remains when we deal with extremes. And this uncertainty carries a profound philosophical note. Even with the most advanced telescopes, the universe doesn't hand us clean answers. It forces us to work with probabilities, with ranges, with models. And perhaps that makes the cosmos all the more fascinating. After all, the mystery is part of the wonder. If there's one tool that has completely revolutionized our ability to study stars like Stephenson 2-18, it's infrared astronomy. Without it, this colossal giant would probably remain almost invisible to us, hidden behind thick curtains of cosmic dust in the Milky Way. You see, visible light, the kind our eyes are sensitive to, doesn't travel well through interstellar space when dust is in the way. Dust particles, often made of carbon and silicates, scatter and absorb shorter wavelengths of light, especially blue and visible photons. That's why the center of the galaxy and regions like the Scutum constellation, where Stephenson 2 to 18 lives, look like dark patches in visible light images. It's not that nothing's there, it's that the light is being blocked before it reaches us. But infrared light behaves differently. With its longer wavelengths, it can slip through dust clouds much more effectively, almost like radio waves passing through walls that stop visible light. That means that while Stephenson 2 to 18 looks dim and hidden in the visible spectrum, it becomes much clearer and more luminous when viewed in the infrared. This ability to see through the dust is exactly why astronomers rely so heavily on infrared telescopes when studying distant red supergiants. Infrared astronomy not only allows us to detect stars like Stephenson 2 to 18, it also helps us understand them in ways that visible light simply cannot. For one, infrared wavelengths give us better information about the temperature of such cool stars. Remember, Stephenson 2 to 18 has a surface temperature of around 3,200 Kelvin, far cooler than the Sun's 5,800 Kelvin. Cooler stars emit much more strongly in the infrared than in visible light, which means infrared detectors are far better suited for capturing their radiation. In a sense, these stars reveal their true selves in infrared. Their peak brightness shifts out of the visible spectrum and into these longer wavelengths. But the real magic happens when infrared is used to study the dust and gas surrounding red supergiants. Stars like Stephenson 2 to 18 shed enormous amounts of material into space through stellar winds. That material forms vast shells or clouds of dust around the star. In visible light, those dusty envelopes obscure the star even more. But in infrared, we can not only see the star through the dust, we can also analyze the dust itself. The dust absorbs the star's light, warms up, and re-radiates that energy in the infrared. By studying that radiation, astronomers can measure the composition, density, and distribution of the dust around the star. This is crucial for understanding how stars lose mass and how they enrich the interstellar medium with heavy elements. Another benefit of infrared astronomy is the ability to map star clusters like Stephenson 2, the group where Stephenson 2 to 18 resides. The entire cluster is buried in dust, invisible to optical telescopes. But in infrared, dozens of massive stars in the cluster suddenly appear. Without infrared, the Stephenson 2 cluster might never have been properly identified, and the discovery of Stephenson 2 to 18 as its largest member might have been delayed or even missed. It's no exaggeration to say that infrared is the key that unlocks hidden stellar nurseries and ancient clusters in our galaxy. Let's also consider the technology that makes this possible. Instruments like the Spitzer Space Telescope and ground-based observatories equipped with infrared detectors have played an enormous role in revealing stars like Stephenson 2 to 18. More recently, the James Webb Space Telescope, JWST, has taken this to another level entirely, with unprecedented sensitivity in the near and mid-infrared. JWST is particularly suited for studying red supergiants, because it can not only cut through the dust but also resolve subtle details about their atmospheres, winds, and circumstellar environments. In fact, JWST could help refine the measurements of Stephenson 2.18's size, luminosity, and even its mass loss rate. Another fascinating point is how infrared spectroscopy works hand in hand with imaging. By breaking down the infrared light into its spectrum, astronomers can detect the fingerprints of specific molecules in the star's atmosphere and its surrounding dust. For example, molecules like water vapor, carbon monoxide, and silicates all emit or absorb at distinctive infrared wavelengths. This gives us clues about the chemistry taking place in and around Stephenson 2 to 18. And chemistry matters, because the elements expelled by stars like this are the raw materials for the next generation of stars and planets. Without the ability to study them in infrared, our picture of how the galaxy recycles itself would be incomplete. So, to put it simply, infrared astronomy doesn't just make Stephenson 2 to 18 visible, it makes it understandable. It allows us to pierce the dust, see the star glowing in its full brilliance, measure its temperature more accurately, analyze the dust and gas it sheds, and place it in the broader context of its cluster and environment. Without infrared, this star would remain a hidden phantom, barely a whisper behind the Milky Way's veil. With it, Stephenson 2-18 becomes the cosmic titan we now recognize as the biggest star ever found. Imagine, for a moment, that Stephenson 2-18 suddenly appeared in place of our Sun. Our familiar solar system, which feels vast and spread out to us, would suddenly look minuscule and fragile compared to this monstrous red supergiant. The sheer immensity of its size is so incomprehensible that the only way to begin to grasp it is through direct comparisons with the orbits of our planets. Let's start small, with the inner planets. Mercury, which orbits at just 58 million kilometers from the Sun, would vanish instantly inside the fiery depths of Stephenson 2-18. Venus wouldn't stand a chance either. Even Earth, our home, orbiting 150 million kilometers away, would be nothing more than a swallowed grain of dust within the enormous radius of this star. In fact, not just Earth, Mars, too, with its more distant orbit, would be deep inside the gaseous, turbulent atmosphere of Stephenson 2-18. If this star replaced our Sun, all 4 terrestrial planets would be obliterated, completely engulfed without trace. But the devastation wouldn't stop there. The size of Stephenson 2-18's radius is around 2,150 times that of the Sun. That's so gigantic that its edge would extend far beyond the orbit of Jupiter. Think about that. Jupiter, the largest planet in our solar system, sitting nearly 780 million kilometers away from the Sun, would still be swallowed whole. Its storms, its great red spot, its moons, all of them would be drowned inside the blazing layers of plasma. Saturn, orbiting at about 1.4 billion kilometers, would also fall victim to Stephenson 2-18's massive reach. Even Saturn's spectacular rings, stretching tens of thousands of kilometers outward, would dissolve within this star's colossal atmosphere. Now here's where it gets truly mind-bending. The star's boundary, if it was centered where our Sun is, would stretch well past the orbit of Saturn and possibly even reach close to Uranus's orbit. That means nearly the entire inner and middle solar system, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and perhaps even Uranus, would lie inside Stephenson 2-18's immense body. Imagine our solar system's majestic gas giants, those worlds that we think of as impossibly big, floating like tiny bubbles in the belly of a monster. Neptune, orbiting at 4.5 billion kilometers, would probably just barely escape, but from its vantage point, the sky would be dominated entirely by the titanic surface of Stephenson 2-18. Instead of a bright point of light, Neptune would see an entire horizon filled by the fiery red glow of this star. And let's not forget the smaller details. Moons like Europa, Titan, and Enceladus, the places where scientists dream of finding extraterrestrial oceans, would be gone, swallowed without hesitation. The asteroid belt between Mars and Jupiter, absorbed. The icy chunks of the Kuiper belt beyond Neptune, some might survive. But they'd orbit under the dominance of a cosmic giant whose influence stretches farther than we can truly picture. To get another perspective, consider this. The diameter of Stephenson 2-18 is estimated at nearly 3 billion kilometers. For comparison, the distance from the Sun to Saturn is about 1.4 billion kilometers. That means this star could swallow Saturn and still have room to spare. If Stephenson 2-18 replaced our Sun, its outer surface would engulf nearly every planet we know and love. Only the most distant outliers, the icy dwarfs like Pluto, Eris, and Sedna, would remain beyond its glowing edge. But here's the kicker. If you could somehow fly a spacecraft around the surface of Stephenson 2-18, just skimming its surface like an airplane circling Earth, it would take you years to complete the journey, even at the speed of light. We'll explore that in more detail later, but it gives you a sense of the vastness of this cosmic body. So the image to hold in your mind is staggering. If Stephenson 2-18 were placed where our Sun is now, the solar system as we know it would cease to exist. Not just Earth, not just the rocky planets, but even the gas giants would be consumed. Imagine looking up at the sky from Neptune and seeing no sun, no stars, only an endless horizon of swirling crimson plasma stretching across your entire field of vision. The Sun, which feels impossibly large and life-giving to us, would be a forgotten speck inside this new cosmic overlord. And this is why the engulfing comparison is so effective. Stephenson 2-18 doesn't just outsize our Sun, it completely redefines our idea of scale. The solar system, which feels boundless, suddenly feels fragile and tiny, all swallowed by one single star. It's not just bigger, it's the difference between an anthill and a mountain range, between a pond and an ocean. When we talk about Stephenson 2-18 as the biggest star ever found, it's important to pause and realize just how tentative that crown might be. Astronomy is not a field where absolutes are easily claimed, because the universe is simply too vast and our instruments, though powerful, are still limited. Calling Stephenson 2-18 the largest star ever discovered is a little like saying we found the tallest tree in an infinite forest. Impressive, yes, but who's to say what still looms just beyond our view? Right now, Stephenson 2-18 holds the record because it has been measured, studied, and placed under the scrutiny of our best telescopes. Its radius of around 2,150 times that of our Sun makes it the reigning giant. But space is incomprehensibly vast. Our galaxy alone contains perhaps 100 to 400 billion stars, and then there are 2 trillion galaxies beyond that. That's a staggering number of stars, many of which are hidden behind curtains of dust, embedded in stellar nurseries, or simply too far away to observe with current technology. The odds that Stephenson 2-18 is the true largest star in the universe are slim. It's more likely that it's just the largest we've seen so far. Consider how discoveries of massive stars have evolved in recent decades. For a long time, VY Canis Majoris held the record for being the largest known star. Then, more precise measurements suggested it wasn't as big as we thought, and UY Scuti claimed the title. But soon after, refined data showed Stephenson 2-18 was even larger. Each discovery is a step forward in accuracy, a correction of the record as our instruments sharpen. This shifting record reminds us that science is always provisional. What seems like the biggest today may be dwarfed tomorrow. This brings us to an exciting thought. What if there are stars even larger than Stephenson 2-18, hidden in parts of the galaxy we cannot yet see? Many regions of the Milky Way are blanketed in interstellar dust, which blocks visible light but can sometimes be penetrated with infrared or radio waves. Even so, our reach is not infinite. Some clusters of stars may lie concealed, harboring giants that make Stephenson 2-18 look almost modest. And beyond our own galaxy, in the dense star-forming regions of other galaxies, who knows what titanic stars may burn, unseen and unmeasured? The potential scale is breathtaking. Stars as large as Stephenson 2-18 are rare, but not impossible. They form in massive star clusters, where gravity and abundant gas allow for the birth of truly extraordinary stellar monsters. Our own galaxy contains only a handful of such clusters. Stephenson 2 is one, Westerlund 1 and 2 are others. Each one could potentially harbor stars close to or exceeding Stephenson 2-18 size. And that's just in our galaxy. Imagine galaxies that are much larger, denser, or more active than the Milky Way. It's conceivable that some of those could host stars even bigger than any we've yet identified. What makes this thought even more intriguing is the nature of astronomy itself. Much of the night sky is still unmapped in detail. Astronomers estimate that as much as 90% of the Milky Way is hidden from direct optical observation because of dust lanes and the sheer distance involved. The galactic core, in particular, is a treasure trove of massive stars, but its heavy obscuration makes it one of the hardest regions to explore. When new generations of telescopes probe these hidden regions with more advanced infrared and radio imaging, we may very well stumble upon stars even more gigantic than Stephenson 2-18. And then, beyond the Milky Way, there are galaxies like the Large Magellanic Cloud or Andromeda, filled with their own populations of red supergiants and hypergiants. Some of these stars could easily surpass Stephenson 2-18 in radius, but they are simply too far away for us to measure with high precision right now. Even the James Webb Space Telescope, as powerful as it is, can only probe so much detail at such distances. But as technology advances, through next-generation telescopes like the Extremely Large Telescope, ELT, in Chile or the 30-meter telescope, TMT, we'll be able to observe stars with unprecedented clarity, potentially rewriting the record book again. It's also worth remembering that the universe is dynamic. Stars like Stephenson 2-18 are living on borrowed time. They will not remain in their bloated red supergiant phase for long, astronomically speaking. This phase is transient, lasting only a few 100,000 years at most, a blink in cosmic terms. That means stars this large are exceedingly rare, both because few stars ever grow this massive in the first place, and because those that do spend such a short time at this size before collapsing. When we find a star like Stephenson 2-18, we are catching it in a fleeting act of its life cycle, like seeing a firework at its brightest just before it fades. Somewhere else, other fireworks may be in bloom, waiting for us to notice them. So when we say Stephenson 2-18 is the biggest star ever found, it's more a reflection of our current knowledge than an ultimate truth. It's the largest star that has revealed itself to us with enough clarity to be measured. But the cosmos is vast, ancient, and still full of secrets. For all we know, there may be stars out there thousands of times larger than the Sun that we haven't yet glimpsed, hidden in the dense stellar nurseries of distant galaxies or lurking behind the thick dust of our own. And this is what makes astronomy so humbling. Every discovery feels monumental, yet it is only a step on an endless journey of expanding perspective. Stephenson 2-18 might be the king of stars today, but the throne is not secure. The universe is a stage too vast for us to assume we've seen the largest actor. Somewhere, in the uncharted depths of space, there may be stars that make Stephenson 2-18 look small, waiting for humanity's eyes to grow sharper and our reach longer. The question that often arises when talking about an extraordinary star like Stephenson 2-18 is this: why does it matter? Why do astronomers dedicate so much time and energy to studying a star nearly 19,000 light-years away, invisible to the naked eye, and destined to explode long before humanity ever develops the means to visit it? The answer lies in what Stephenson 2-18 represents. It is not just a giant ball of gas burning in isolation, but a cosmic laboratory, a living snapshot of some of the most extreme processes in the universe. By studying it, we're not just cataloging a curiosity, we're unlocking the story of how stars live, die, and ultimately shape the very matter that makes up planets, life, and even us. At its heart, astronomy is about understanding our origins. Every atom of carbon in our bodies, every oxygen atom we breathe, the calcium in our bones, the iron in our blood, all of it was forged in the hearts of stars and scattered into space when those stars died. Stars like Stephenson 2-18 are especially important because they represent the final, most dramatic stages of stellar evolution. They are factories on an immense scale, creating and redistributing heavy elements that become the building blocks for future generations of stars and planets. Without the explosive deaths of giants like Stephenson 2-18, the universe would be a much poorer place, literally, in terms of chemical richness. Studying Stephenson 2-18 also helps astronomers test the limits of physics. Stars cannot just grow infinitely large. There are delicate balances at work, the inward pull of gravity trying to collapse the star, and the outward push of radiation pressure from nuclear fusion fighting against it. Stephenson 2-18 is so big that it pushes right up against those limits. By observing it, we learn how nature balances these forces in extreme environments. We can see how far a star can expand before it becomes unstable, how its outer layers respond to this expansion, and what happens in its core as it approaches collapse. This teaches us not only about red supergiants, but about the physical laws that govern matter on a cosmic scale. Another reason stars like Stephenson 2-18 matter is because they are a glimpse into the future of stars. Our Sun will never become this large. It will end its life as a red giant far smaller than Stephenson 2-18, and then quietly fade into a white dwarf. But massive stars live very different lives, burning hotter, faster, and dying in explosive events that reshape their surroundings. By studying Stephenson 2-18, astronomers gain insights into what happens to the universe's most massive stars, and how their deaths seed galaxies with new material. These deaths also trigger the formation of new stars by compressing gas clouds, making them critical players in the cycle of cosmic evolution. Stephenson 2-18 is also important for another reason. It challenges our models. For decades, astronomers have used computer simulations to predict how stars evolve. But sometimes reality doesn't match the models. Stephenson 2-18 is so vast that it stretches the limits of what those simulations say should be possible. That means there's still much we don't understand about how stars behave at this scale. Perhaps there are processes in its interior that we haven't fully accounted for, complex mixing of gases, turbulent convection, mass loss through stellar winds. Every new piece of data on this star forces us to refine our theories, making them stronger and more accurate. And then there's the question of its death. Stephenson 2-18 will not go quietly. It will end in a cataclysmic supernova, or even a hypernova explosion. Studying it today allows us to anticipate what such an event would look like and prepare for the day when one of these titans in our galaxy does explode. A supernova of this scale would outshine the entire galaxy for weeks or months. If it happens close enough to Earth, not Stephenson 2-18 itself, since it's too far to harm us, it could be visible even in daylight, an event of staggering beauty and scientific opportunity. Understanding how a star like Stephenson 2-18 lives helps us interpret the signals we'll see when it finally dies. These kinds of studies are also tied to one of the biggest mysteries of modern astrophysics: black holes. When a star as massive as Stephenson 2-18 collapses, it may leave behind not just a neutron star, but potentially a black hole. Observing giants like this helps us predict the kinds of black holes they might produce, their masses, and how often such black holes might form in the galaxy. Since black holes themselves can't be observed directly, studying their progenitors, the stars that give birth to them, is one of the best tools we have for understanding them. There's also a practical, forward-looking reason why Stephenson 2-18 matters. Humanity is still at the dawn of exploring the universe. Our descendants, centuries or millennia from now, may look back on the data we collect today as the first seeds of knowledge that allowed them to harness, navigate, or survive the extreme environments of stars. Understanding stellar evolution is not just abstract science. It could one day be the difference between survival and extinction if humanity learns to live among the stars. And finally, there's the matter of perspective. Stephenson 2-18 reminds us of our place in the universe. It dwarfs our Sun, which itself sustains all life on Earth. If our Sun feels impossibly large to us, Stephenson 2-18 makes it look like a mote of dust. And yet, even this colossus is but one star among billions in our galaxy, which itself is one among trillions. Studying such stars humbles us. It reminds us that the cosmos is not centered around us. It is vast, ancient, and full of wonders beyond comprehension. And in that humility lies inspiration. The fact that humans, tiny beings on a small planet, can look across thousands of light years to measure and study a star like Stephenson 2-18 is itself a miracle of intelligence and curiosity. So why does Stephenson 2-18 matter? Because it holds answers to some of the deepest questions we can ask. How do stars live and die? Where do the elements come from that make us who we are? What happens at the very limits of physics? And what might still lie undiscovered in the uncharted reaches of space? To study Stephenson 2-18 is to study ourselves, our origins, and our future in the cosmos. Here's where the imagination truly shatters under the weight of scale. We've already talked about how Stephenson 2-18 would engulf our solar system if it sat where our Sun is, but there's a statistic so staggering, so utterly beyond human experience, that it feels like something out of science fiction. If Stephenson 2-18 were a hollow sphere, you could fit not just a few suns inside it, not just a handful, not even a million, but more than 10 billion suns could fit within its volume. Think about that for a moment. Our Sun, a colossal ball of plasma 100 times wider than Earth, feels impossibly huge. Yet inside Stephenson 2-18, it would be like tossing a grain of sand into a cathedral. Not just one grain, either, but billions of them. Imagine row upon row of suns, filling the vast interior, 10 billion of them sitting comfortably inside this one red supergiant, with room to spare. That number alone is enough to leave the human brain reeling. Now let's try to break it down into something slightly more tangible. 10 billion is such an absurdly large number that our minds struggle to grasp it. If you were to start counting suns, one every second, how long would it take to count to? 10 billion? The answer: more than 300 years. Imagine passing the task of counting down through generations, centuries of humans whispering 1, 2, 3, without sleep, without pause, and only then reaching the number of suns that could fit inside Stephenson 2-18. That's how enormous it is. To put it another way, the volume of Stephenson 2-18 is estimated to be about 10 quadrillion times larger than Earth's volume. That number is so large it makes Earth, the planet that holds oceans, continents, mountains, and billions of people, seem microscopic. Our planet wouldn't just be swallowed, it would vanish into insignificance, lost among billions of other Earths that could also fit inside this monster. But perhaps even more powerful than the numbers themselves is the mental image. Imagine lining up suns like glowing marbles, each one blazing with nuclear fire. You could pile them in layer upon layer, like cosmic cannonballs, and you'd still need billions more to fill Stephenson 218's cavernous interior. If you looked at it from the outside, Stephenson 218 would still appear like a single star in the sky. Yet inside, hidden beyond its edge, lies enough space to house 10 billion stars the size of our Sun. This fact also highlights an important point. When we talk about biggest star, we don't necessarily mean it has the most mass. Stephenson 218 is so extended and inflated that it covers a mind-boggling volume, but much of that space is not densely packed. Its outer layers are spread thin, almost ghostly in density, which is why it can balloon out to such extremes. It's like comparing a dense bowling ball to a gigantic soap bubble. The soap bubble takes up far more space, but the bowling ball contains far more weight. In Stephenson 218's case, it's the soap bubble of the cosmos, thin and tenuous, but impossibly large. And yet, the fact remains, no matter how you frame it, the volume alone is enough to make Stephenson 218 the undisputed king of size. 10 billion suns. It's the kind of number that makes you pause, sit back, and accept that we humans are not wired to truly comprehend the universe's scales. We can measure them, we can express them, but to feel them is like trying to hold the ocean in the palm of your hand. Here's a thought experiment that really drives it home. If Stephenson 218 were hollow, and you placed our Sun at the center, and then started arranging other suns around it to fill up the space, the edge of this star would still lie billions of kilometers away. You could keep stacking suns like Lego bricks, row after row, until you reached 10 billion, and only then would you run out of room. The sheer emptiness within its boundaries is as overwhelming as its size. And remember, this is just one star. One star among billions in our galaxy. A galaxy that itself is one among trillions in the universe. If just one star can contain billions of suns, what does that say about the richness of creation spread across the cosmos? Stephenson 218 is not only a record-breaking marvel, it's a humbling reminder that the universe operates on scales far beyond human imagination. There's a natural temptation, when hearing about Stephenson 218, to ask, could there be something even larger? Could stars keep on ballooning endlessly, until their atmospheres stretch across solar systems like cosmic leviathans with no bounds? The answer is both fascinating and sobering. No, stars cannot be infinitely big. And the reason lies in the delicate and relentless tug-of-war between two colossal forces, gravity and radiation pressure. At the very core of every star, nuclear fusion is the engine that powers it. Hydrogen atoms slam together under immense pressure and temperature, merging into helium and releasing extraordinary amounts of energy. This energy doesn't stay bottled up, it streams outward, exerting an outward push we call radiation pressure. This outward pressure pushes against the star's own immense gravity, which is always trying to crush it inward. The result of this eternal battle is equilibrium. The star maintains its shape because gravity and radiation pressure balance one another almost perfectly. But here's where the limits come in. Gravity is straightforward. The more mass you pile into a star, the stronger its gravitational pull becomes. But radiation pressure doesn't scale in the same way. As the star grows larger and its fusion becomes more intense, the energy pushing outward increases dramatically. At some point, if the star swells too large, its outer layers become so loosely bound by gravity that the radiation pressure can begin to blow them away. The star starts losing mass in powerful stellar winds, sometimes shedding entire layers of its outer atmosphere. This is why stars like Stephenson 218 can become staggeringly big but not infinitely so. It is inflated to a radius more than 2,000 times that of the Sun, but beyond that, its outer layers are so tenuous and fragile that they can barely hang on. In fact, Stephenson 218 is already shedding mass at a furious rate, casting off material into space in a kind of stellar exhale. These winds enrich the surrounding interstellar medium with heavy elements, but they also signal that the star is approaching its physical limits. If it tried to expand much farther, those delicate outer shells would simply drift away, leaving behind a somewhat smaller but still titanic core. There's another factor at play too: temperature. A star's surface temperature influences how much radiation pressure it exerts. Massive red supergiants like Stephenson 218 are relatively cool on the surface, around 3,200 Kelvin, compared to our Sun's 5,778 Kelvin. This cooler surface means their light output per square meter isn't as intense, But because the surface area of a star like Stephenson 2-18 is incomprehensibly vast, the total energy flowing outward is still colossal. The balance point, the place where expansion halts, is set by this interplay of pressure, temperature, and gravity. There's a theoretical ceiling known as the Eddington limit, the point at which the outward pressure of radiation becomes strong enough to blow away a star's outer layers faster than gravity can hold them. While the exact value depends on the mass, luminosity, and composition of the star, Stephenson 2-18 and other red supergiants hover dangerously close to this boundary. They're literally stars living on the edge, their atmospheres trembling on the brink of being cast into the void. This balancing act is why we don't see stars 1,000,000 times the size of the Sun, or ones stretching across entire galaxies. Physics doesn't allow it. Nature's laws draw a line. Stars can only get so big before they collapse under their own weight or peel themselves apart. Stephenson 2-18 represents one of those natural extremes. It's the largest known red supergiant because it has reached that precarious edge and swollen to the maximum extent allowed by the universe's rules. And yet, this limitation is not a weakness, it's what makes stars so fascinating. Because they cannot grow infinitely large, stars live within a predictable framework. Their life cycles, from birth to death, follow paths we can trace and understand because they are bound by these physical laws. When Stephenson 2-18 dies in a supernova, it will obey the same rules as countless other massive stars before it. Gravity will eventually win, pulling its core inward until it collapses into a neutron star or black hole, while the outer layers erupt outward in a catastrophic explosion. So, in the end, the limits of physics are what give us the incredible diversity of stars across the universe. Without them, stars might simply balloon endlessly or collapse instantly. Instead, we get a spectrum, from tiny red dwarfs to titanic giants like Stephenson 2-18, each living out its life on the knife edge between gravity and radiation pressure. Stephenson 2-18, in all its immensity, is a testament to how far those limits can be stretched, and a reminder that even in a cosmos of almost unimaginable scale, there are still boundaries dictated by nature's fundamental forces. As we near the end of this journey across scales so vast that even numbers strain to contain them, it becomes clear why Stephenson 2-18 holds its throne as the reigning monarch of stars. In a universe that teems with unimaginable wonders, black holes that can devour suns whole, galaxies that span hundreds of thousands of light-years, quasars that outshine trillions of stars, there still remains something uniquely awe-inspiring about a single star that dwarfs everything we've ever measured. Stephenson 2-18 is not just large, it is, as of now, the largest star ever discovered. It wears this crown not because of its mass, for we know there are heavier stars, but because of its sheer, staggering size. With a radius over 2,000 times that of the Sun, Stephenson 2-18 expands across a volume so immense that if placed where our Sun is now, its surface would swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn, and stretch well into the realm of Uranus. Its radius alone breaks every mental boundary we hold for what a star can be. And in volume, the numbers simply border on the incomprehensible. Over 10 billion suns could fit inside it. That one fact alone is enough to secure its title as the current king of cosmic giants. It also dethroned what was once considered the undisputed titan, UY Scuti, proving how science constantly evolves with better instruments, sharper observations, and deeper understanding. UY Scuti had long held the crown, but Stephenson 2-18 revealed that the universe still had a grander contender waiting in the shadows, hidden in the dense fields of the constellation Scutum. That discovery was not only a triumph of observational astronomy, but a reminder that even our best assumptions are only temporary in the face of cosmic truth. Its identity as a red supergiant also plays into its uniqueness. These stars represent the final, swollen breaths of stellar evolution, the last chapters before the inevitable collapse. That Stephenson 2-18 has managed to balloon to such an outrageous size without yet imploding is a testament to how finely tuned the balance of forces within it must be. It is a living paradox, impossibly massive, yet fragile, vast beyond imagining, yet tenuously held together by the thin thread of equilibrium between gravity and radiation. The fact that we can't see it with the naked eye despite its immensity adds a kind of cosmic irony. Here is the largest known star, a body that dwarfs even the wildest creations of human imagination, and yet it's invisible to us without the aid of telescopes and infrared instruments. It lurks in obscurity, hidden behind dust clouds, quietly existing as a record holder while our eyes scan the skies for lesser giants like Betelgeuse. Its invisibility makes it feel like a secret of the universe, a treasure uncovered only through patience and persistence. And perhaps most important of all, Stephenson 2-18 embodies the limits of stellar physics. It shows us how far nature can stretch the rules without breaking them, how stars cannot expand forever but instead hover near the razor's edge of collapse. Its immense size tells us not just about itself, but about the processes that govern the birth, life, and death of all stars. From the smallest dwarfs to the largest supergiants, they are bound by the same dance of gravity and fusion, pressure and collapse. Stephenson 2-18 stands as a monument to those laws, a red supergiant, swollen to the maximum extent possible before physics draws the line. This is why, for now, Stephenson 2-18 is king. Not just because it is the biggest we've ever found, but because it crystallizes everything we know about the life cycles of stars, the challenges of astronomical observation, and the sheer audacity of the universe's scale.
It humbles us.
It forces us to step back and admit that our solar system, our sun, our Earth, even our very existence, is a whisper against the backdrop of such cosmic immensity. But kingship, even in the cosmos, is not eternal. Stephenson 2-18 will not last forever. One day it will collapse under its own weight and explode in a titanic supernova or hypernova, scattering the elements forged in its core across the galaxy. Its reign as the largest star will end, both in physical existence and perhaps in title, should astronomers discover an even bigger one lurking in some distant corner of the Milky Way or another galaxy. And that possibility, that the universe might still hide stars larger than even this, is perhaps the most thrilling fact of all. Somewhere in the infinite canvas of the universe, where galaxies swirl like cosmic whirlpools and clusters of stars sparkle like scattered jewels, Stephenson 2-18 stands as a staggering reminder of just how small we really are. We began this journey by asking a simple question: what's the biggest star in the universe? And along the way, we've been forced to stretch our imaginations, to try and wrap our minds around scales so immense that even light itself, the fastest traveler we know, would take nearly a decade just to complete a single lap around this colossal star. Yet despite everything we've learned, despite the mind-bending comparisons and the sheer mathematical enormity of its size, Stephenson 2-18 is still just one chapter in an unfinished story. For all its grandeur, for all the records it currently holds, it is but a single star among billions in our galaxy, and trillions upon trillions across the cosmos. The very fact that we discovered it tucked away in the obscured dust lanes of the constellation Scutum, invisible to our naked eyes, raises a tantalizing question. How many more are out there, hiding just beyond the reach of our instruments, waiting for their turn to be unveiled? Astronomy has always been about peering into the unknown, using light as a messenger across the abyss of space and time. Each discovery, whether it's a star bigger than our minds can process or a galaxy older than the universe was once thought to be, reminds us that the cosmos is not finished revealing its secrets. Stephenson 2-18's immense scale doesn't close the book on the search for cosmic giants, it opens it wider. If such a titan can exist unseen until the 21st century, what does that say about the countless stars lying hidden in galaxies millions of light-years away? This is what makes Stephenson 2-18 so extraordinary, not just its size, but its symbolism. It represents both a boundary and a promise. The boundary of what we currently know about stellar evolution, and the promise that there is more, much more, still waiting beyond the horizon of discovery. One day, perhaps tomorrow, or perhaps centuries from now, astronomers may find a star that dwarfs even Stephenson 2-18, forcing us once again to update our cosmic records. And when that day comes, it will be yet another reminder of the universe's infinite capacity to humble and astonish us. So as we leave this journey, let's hold on to the image of Stephenson 2-18, a red supergiant so massive that our sun becomes a mere speck in comparison, a star so vast it could swallow our solar system whole, and yet one that lies hidden in the dust of the Milky Way, invisible to the unaided eye. It is a king among stars, a titan of the cosmos, and a symbol of the unimaginable grandeur that lies beyond our reach. The universe is vast and full of wonders. Stephenson 2-18 may be the biggest star we know, but what bigger giants are still waiting to be discovered? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.